Hello, everyone. Welcome to the course, Physics Behind the Quantum Internet, a gentle introduction. I'm Michael Raymer, and I would like to welcome you to the first presentation of the Winter School on Quantum Networks, sponsored by the Center for Quantum Networks. The Center for Quantum Networks is a funded research center supported by the National Science Foundation under the Engineering Research Centers program. And the goals of the Center for Quantum Networks are to carry out basic research and engineering development to support the development of a quantum internet. And in this short course today and the ensuing ones during the rest of the week, you'll learn a lot of the physics, computer science, and mathematics and engineering and optics that go into this very challenging effort. So the Center for Quantum Networks is organized and led by the University of Arizona, with the following other universities in the United States supported and active in the program: MIT, Harvard, Yale, Northern Arizona University, University of Massachusetts at Amherst, Howard University, University of Oregon, where I'm located, University of Chicago, and Brigham Young University. So on to the course. This course is co-developed and co-presented by myself and Abby Gookin. And you'll see Abby in a few minutes, or she might be on screen now. Abby is an undergraduate student at the University of Arizona, majoring in systems and quantum engineering. So she will be helping to operate the Zoom polls and also jumping in if I make a mistake, and she'll correct me. And then later on, she'll also be presenting part of the lecture material. So for those who are interested in a somewhat of a deeper dive into the physics underlying today's course, there's a book that I authored a few years ago, shown on the screen here, and it's available on many online book dealers. But today's course is meant to be self-contained, regardless of the book. So the first poll question is the following: what is your highest level exposure to quantum theory? So Abby will now activate the poll question. There it is. You can grab the poll box in the upper right, in the top, and move it to the upper right-hand corner of the page to get it out of your way. You can also resize the box to some extent by grabbing on the bottom and pulling it. You'll have to move this box every time a poll question comes up. So please click on one of those four boxes, and Abby will monitor the incoming responses, and then we'll discuss that. And so 3 more seconds. So let's go ahead and Abby, do you have enough responses?
Yes, Mike, we do.
So please go ahead and close the poll and show the responses. Very nice. So we have many people spread around the different levels of exposure to quantum mechanics. And I see there's a good number of people that have had college exposure. So that's great. I want to say this course can be useful for all of you, those who are completely new to quantum theory, or those who learned the Schrodinger equation, but not anything about quantum information theory. Or finally, for those who have more exposure to quantum theory, but are curious about effective ways to teach quantum information to non-experts. We'll try to model that. So the course is broken into 4 parts. We'll spend 3.5 to 4 hours maximum on this. The first part is quantum information theory. Then we'll talk about encoding and transmitting quantum information, then Bell state measurements, and then we'll put it all together and describe how you can build a quantum internet, which of course does not exist yet. That's future technology, near future, we hope. Okay, so the first part, quantum information science. Just to give you some background before I launch in, this shows Professor Chris Monroe of Duke University and myself about 5 years ago, we went to Washington, D.C. and lobbied the U.S. Congress and successfully inspired them to pass the following act, which is called the National Quantum Initiative Act. And this, since it's been funded by the U.S. government, it's provided several $billion for basic research and engineering research to try to move forward all the subjects of quantum information science. And the way that one explains to a general audience, like politicians, what is quantum information science and technology is in the following three pillars. The first one is quantum computing, which we won't discuss in great detail in this winter school, because the winter school is focused on quantum communication. But of course, quantum computing in some sense is the most widely known application of quantum information science. There's also quantum sensing, which is very important in many technical areas. You can see the applications listed here. The third one, which we'll focus on today, is quantum communication. And quantum communication enables and links together all of these different quantum technologies. And so we'll discuss some of these, but not in detail. So for example, secure data encryption, remote quantum computing, whereby a user can access a quantum computer from a long distance, distributed quantum computing, where there might be more than one quantum computer working in tandem, distributed sensing, where you take some of these sensors developed as point-like sensors and you connect them to far-flung locations on a quantum network. And finally, you can have multi-party entangled protocols such as secure voting in principle. All these things are far in the future and rely on us developing the necessary hardware and software to operate these systems. So let's go back to the very beginning of this scientific subject. Give me 1 second here. So what is information? If we talk about quantum information, what is information in general? Well, what is classical information? This is what we refer to as the information that's processed and transmitted by the current day computers and networks, and even looking, if you read a book, you're looking at letters, symbols, that we consider those classical information. And there's two types of information. You're probably more familiar with what we call semantic information. That's the meaning of the message that you receive. If you receive an email that says, "I'll be late today," you know what that means. But from a technical point of view, the computer systems don't care about the meaning. They only care about the technical information. That is the actual set of symbols that are sent. And as I'm sure you know, symbols are not sent as letters, but they're sent as zeros and ones. And these are called bits. And for example, if you want to encode the number 2, then you put a series of 8 zeros and ones in this pattern. And this is just binary mathematics. 8 bits is equal to 1 byte, of course. So these zeros and ones are binary. That means there's only 2 possible values. And this is how technical information is transmitted and stored. Well, let's get a little more physical here. In order to actually store or transmit a bit, you have to have a physical device or physical object that physically encodes the bit. And it's convenient to talk about a light switch. So if the light switch is up, we call it a 1. If it's down, we call it a 0. And it's this or that. It can't be both at once, of course. A switch is a switch. Okay. We call the condition of the switch the state. So if the switch is up, we call the state equal to 1. If the switch is down, we call the state 0. Now let's do a poll question here. Put that one up, please. So let's consider a classical memory cell that has 2 light switches. So imagine you have a wall in your room and there's 2 light switches side by side. That's considered one memory cell. Now, please answer the question, how many possibilities, combined possibilities, are there for this combined set of 2 switches? Please answer that question. Okay, 5 more seconds. Okay, let's reveal the results. Okay, most people said 4, and that is exactly correct. And the reason that is correct is because you could have both switches up, both switches down, or one up and down, or one down and up. So that's 4 combined combinations. And here they are, both down, one down, one up, one down, or both up. So as a combined object, there are four possible classical states. And here's a picture showing all four of those possible states. Now, this combined set of two switches can only store one of these states at a given time. One of the four states can be stored, one or the other, but not more than one at a given time. That's the nature of classical memory. What if there are three switches? Let's show a poll question for this one. How many unique combinations are there? Please answer this. Five more seconds. Okay, we'll end that poll. Show the results. Okay, most people said 8, and that is absolutely correct. Now, the reason it's 8 is because there's two possibilities for the first switch, times two possibilities for the second switch, times two possibilities for the third switch, and that product equals 8. One way to think about it is you look at the first two switches. Here's the first two switches. There's four combinations of those, and for each combinations of those, there's two settings for the third one. So 4 times 2 is 8. Another way to look at it. And if you have n switches, like for example, if you have 7 switches, there's 128 possible combinations. But of course, you can only store one of those possibilities in a given configuration or memory cell at a given time. You can change it later, but of course, at a given time, only can store one. Okay, so now recall what we just talked about. This bit, now I'm just showing here one switch, don't be confused. There's no green box around this. So this does not represent two switches on a wall. This represents only one switch on a wall, but I'm showing the two possible states. It's 1 or 0. Now, what if I have one single quantum memory element? Here it is. It can be up, 1, or it can be down. But in quantum physics, we can also have what's called superposition. So we denote superposition by a plus sign. It doesn't literally mean you're adding together two things. It's not physically. It's just a notation, but it means that two possibilities exist upon measurement. So if I have this quantum superposition of, I have one switch, it's in the superposition state, which we call 1 plus 0, or the famous Paul Dirac used this funny bracket notation, 1 plus 0. I'll use parentheses here, not the brackets. Now this is one qubit, and it's in a state that's indeterminate. You can't say what it is. You know what the state is. It's 1 plus 0, but you can't say what the value is until you actually measure it. When you actually make the measurement, it reveals one of the two possibilities. So the value of the switch that's revealed is actually, in a way, produced or created during the measurement process. It doesn't have a pre-existing value. Okay, so here's a single switch, as I showed before, up versus down, or 0 plus 1. Okay, but now if I have two switches, I have two quantum switches in this purple box, and these two quantum switches are in some kind of a physical device. We'll give examples of quantum switches later. And we have two of them. So now each of them can be up or down, but we now have a combined state, which I represent by an ampersand. So ampersand means and, or it means in combination with. So we have qubit A is in some state, combined with qubit B is in some state. Okay.
All right, and Mike, we actually have a couple questions over in the Q&A box, and you touched on it a little bit.
Yes.
We have Bob over here asking more about intermediate, transition, and indeterminate states.
Well, indeterminate state, as I used that word earlier, means that we have a superposition, but the value is indeterminate before we make the measurement. I would say the state is not indeterminate. If the state is 0 plus 1, that's a definite state, and you can know that state exactly. You can prepare a qubit in the state 0 plus 1. So the state is definitely given. It's only when you make the measurement that you can get results that are two possibilities and they're indeterminate before you make the measurement. Is that sufficient?
Yes, thank you.
Thank you. Okay, so here at the bottom of the page, now we have two switches in this purple box, but the combined pair of switches can be in a superposition state. So this notation we're going to use throughout the course is very important. We have qubit A combined with qubit B, or and we have plus, which means in superposition with qubit A combined with qubit B. Could be a different state. And you see here, for example, I have up and down in superposition with down and down, just as an example. So this is called an entangled state. And this is the key concept. And it's very abstract. And if you've never seen this before, then I expect you to be puzzled. If you're not puzzled, then you haven't understood what we're trying to explain. So it's like a loop here. You get puzzled, and then the more you learn about it, the less puzzled you are. And then you learn more about it again, and you get puzzled again. And currently, you might know that, in fact, the Nobel Prize was given only a few months ago for people who did experiments, because they were so puzzled over the past 50 years, they had to do experiments to see what was really going on. And you can't figure this out just by pure philosophy or making guesses. You have to do the experiments. And these three scientists were awarded the Nobel Prize for proving that the quantum theory correctly predicts the behavior upon measurement when you have two objects that are in such an entangled state. And this is the key concept that drives all of quantum computing and all of quantum communication. So what does a real qubit look like? Here is an example of a series or a collection of 51 individual atoms. They're called ions because one of the electrons has been stripped off, leaving the atom with an electric charge, which makes it easier to trap it and hold it into a position. And so you can actually line up some number of ions like this. So each of these little dots is a single atom, and this is an actual photograph taken with an actual camera. So if you illuminate these ions with laser light as a certain frequency, each ion can scatter enough light to form an image on an actual camera. You can even see it with your own eye if you look through a microscope. So you can actually see individual atoms. Now, each ion or atom has an electron inside of it, and it's spinning. And you can think of it as spinning clockwise or counterclockwise. So I'm going to cheat here a little bit and represent these spinning electrons as these little tops. These are actually little tops that you can buy as toys, and they're very nice little metal tops. Now, I show one is spinning clockwise, CW, but I'm also showing the same electron could alternatively be spinning counterclockwise. So that's what we call the state of the spin, or the spin state. Okay. Now, we can have superposition. For a given electron spinning inside an ion, that electron can be put into a superposition state in which it has both possibilities for spinning clockwise and possibility for spinning counterclockwise. Again, a real top could never be put into this kind of a state, showing these small metal tops. That's impossible. But for a single electron, it's a quantum object, and it can be put into such a quantum state, which we also call a non-classical state, because there's no counterpart to this state in ordinary classical physics, or even in common sense, or in your intuitive thinking about large objects, but it does apply to single electrons. Okay, so here I attempt to explain what happens when you measure this. So let's say that we take this electron and we prepare it in a spinning state clockwise. Now, the way we do this, I'm not going to tell you, but it has to do with lasers and microwaves and so on. You can actually prepare the state. So you have a definitely known state, and that state is spinning clockwise relative to this vertical dotted line, which we call the rotation axis. Okay. If we measure it along this axis, we will get clockwise with 100% probability, because we know what the state is, we can predict it. Now, if we take that electron, we prepare it spinning clockwise along a 90-degree rotated axis, a horizontal axis, and then we measure it along the vertical axis, we'll get 50-50 probability to observe it spinning clockwise or spinning counterclockwise around the vertical axis. Again, there's no classical counterpart to this. This is pure quantum mechanics. A third example, if we prepare the spin so it's clockwise spinning around the 30-degree rotation axis and measure it in spinning which way it spins around the vertical axis, we'll get what 80% probability we'll see it spinning clockwise, and 20% probability spinning counterclockwise. Now, why is it 80%? Why is it 80% greater than 20%? That's because this is a 30-degree axis, which is closer to the vertical. So it's closer to the original preparation direction than is the horizontal. So that means there's a higher probability. It has a more similarity to spinning clockwise this way when it's been tilted only 30 degrees. Okay. Now, if we prepare on the 0, namely the vertical axis, as shown in the picture, and then we measure it on a 30-degree axis, we'll again get 80% and 20%. So that's kind of the opposite case from the one I just showed up here. Okay,
Mike,
so
we also
yes.
do one more question. Are ions positive or negative charges? David asks.
Well, so we have a neutral electron. We remove one we have a neutral atom. We remove one electron, which takes away a negative charge. So we're left with a positively charged ion.
Perfect. And another question we have is there a simple closed form expression relating to the probabilities? Is the 80-20 a fixed rule or just an example here?
I will show the exact formula in later in the slides. Thank you.
Thank you.
Okay, so what does superposition mean? It does not mean both at the same time. It doesn't mean that it's spinning both clockwise and counterclockwise at the same time. And it also doesn't mean or. It doesn't mean it's spinning either or clockwise or spinning counterclockwise. It really is some completely different philosophical concept or even physical concept than you would have in common sense. So what it actually means is it only has to do with how you can predict the outcomes of the measurements. And you can't really say in common sense what it means physically. This is the way the world works. And we know it works this way because we do experiments and we observe it. It really works that way. And I'll give the formula exactly later. So this clockwise around the vertical axis means that if you measure it later, you'll get this 80% and 20%. But notice if you measure it on different axes, you'll get different probabilities. So again, it does not mean that it's spinning a particular direction before you measured it. It's really indeterminate. You could say that it's a wrong question. It's not you can ask the question, but the question doesn't have an answer. So we call it an ill-posed question. Namely, which way is it really spinning before you measure it? That's an ill-posed question. The only thing you can answer is what happens if I measure it, I get this or that. So don't ask questions that have no answer. Okay, now what if we do a sequence of measurements? What if we first have our spin, so it's spinning clockwise around the vertical, and then we measure it on a 30-degree axis. As I said before, you get 80% chance that it'll be clockwise around 30 degrees, and 20% chance it'll be counterclockwise. So let's say we did that experiment and we observed it this one time, spinning clockwise. What if we observe it again around the same axis, the same 30 degree? Well, now it's going to be 100% clockwise because you already determined by the first measurement. I shouldn't say determined. That's wrong. You didn't actually make a measurement. By doing the experiment, which we call a measurement, you're actually forcing the electron to decide, in a funny way of saying it. You create the measurement result upon the measurement. So once you've created that result or produced the result, or we call the outcome, and you do it again on the same axis, you're guaranteed to get the same result as many times as you keep measuring it on the same axis. But now if I measure it on a different axis, I get back to probabilities again. So you can have a sequence of measurements and you can use probability theory to predict the probabilities of a sequence of outcomes. All right, here's a poll question. Yes.
Before we do the poll question, we do have a couple questions on the last few slides.
Okay.
Bob asks, is this an accurate physical explanation or are these just abstract concepts that we're calling spin, angle, etc.? And why is it only in 2 dimensions rather than 3?
Oh, it is in 3 dimensions. You could rotate these measurement axes to a direction out perpendicular to the computer screen here. So you can do this all in 3 dimensions. And the mathematics is a completely abstract description. Okay, but really any description of anything is abstract if you really get philosophical about it. In classical physics, we have the nice coincidence that our abstract description of a state, like, is a switch up or down, that's still a description. That's still a person thinking about what they think the state is. And that's still probability theory. It's just that in classical physics, you can think of the probabilities and the description as corresponding directly to what the system is actually really doing. But in quantum mechanics, there is no actually really doing behind the scenes. The only thing you can describe is what happens upon a series of measurements to a system. And the abstract mathematics perfectly predicts the probabilities of seeing a particular sequence of measurement outcomes. So it's the measurement outcomes that are real. And what's happening behind the scenes before the measurement is not really real in some sense. That's the most common interpretation, but other people might quibble with that.
Okay, our next question is, we just have a couple, so we can go through them now. Renam asks, how do we know this is the behavior before we measure it?
Oh, we don't unless we prepare it. So the word up here is prepare. So you have to do something with lasers and microwaves in order to prepare the state in a way that you know it is. And now you can verify that if you think you've prepared it in the clockwise direction, in the vertical direction, you can verify that by measuring it in a vertical direction. And then you get that result. So you've confirmed it. And now you can do this measurement along a different axis. So two steps. You can first prepare it by known procedures, and you can check it or verify it by making a measurement. And then you know what's happening. You know now the state, which is a description. This is the best possible description of the condition of that electron, which then allows you to make measurements in the future. Any more?
Yes, our last one is, what physically defines the rotation axis?
Oh, you define that. You are in control of preparation and measurement. So you are a quantum physicist and you have your hands on lasers and microwaves, and you can control that. You can rotate that to any angle you want and make the measurements. We'll give other examples later having to do with light polarization. And for that, think about a pair of polarized sunglasses. If you take sunglasses and take them off your face and you rotate the sunglasses by 90 degrees, you're changing the measurement axis of the polarized light, and you block it or you don't block it. So you are in control of that. Any more?
We have a couple questions that don't really relate to this content, so
okay, let's move on.
Yeah.
Hold those questions for much later, perhaps. Or maybe Abby can answer them in the chat.
Yes, yeah.
Okay, so poll question 4. Actually, Abby has to now activate poll question 4. So this question, move the box away. It's what we just did, but just the different case. Let's say we had prepared the electron in counterclockwise vertical. We measured around 30 degrees, and we happened to get counterclockwise in this particular trial. Now, if we measure it again around the same 30-degree axis, what are we going to observe? Here are the possibilities, A, B, C, D. Please click on one of the 4 answers. Five more seconds. Okay, close that poll. Okay, most people said counterclockwise, 100%. Let's see if that's correct. Well, the hint is repeated like measurements give the same outcome. So yes, it is again. And you could continue that measurement procedure as many times as you want, and you always get the same result, as long as you measure it on the same axis. In some sense, you can think of this 20% probability event as preparing a new state. You see, you started with a with a clockwise in the vertical axis, and by sheer luck, 20% luck, you ended up with a state that's now been prepared in a new state, which is counterclockwise along the 30-degree axis. So this is how quantum measurement works. The word measurement is actually the wrong word, because measurement implies you're revealing a predetermined value of something. But you can see that's not the case here. So the word measurement that's why I call it quantum measurement. It's not the same as classical measurement. Okay, now let's consider entangled state of two ions. So here we have what I call Alicia's ion, and here we have what I call Bob's ion. They're two separate ions. They're in the same vacuum chamber, but they're not the same ion. Well, they can each be put into a superposition state, clockwise in superposition with counterclockwise, like that. And here are four possible combined states. As an example of a combined superposition state would be clockwise and clockwise in superposition with counterclockwise and counterclockwise. This is kind of like 0 and 0 in superposition with 1 and 1, you see. And in general, we could actually have all four possibilities in superposition. And in fact, we could even put different probability factors in front of all these, as we'll show in a second. Here they are. Let's say we have this state with all four possible combined states, 0, 0, 0, 1, 1, 0, 1, 1. But now we're going to multiply each one of those by a number, x, y, z, or w. These numbers correspond to the probabilities. They determine the probabilities. Somebody earlier asked, is there an exact formula? The answer is yes, and I'll show that on the next slide. So let's make a measurement. Given this state, let's say somebody prepared that state for you, and you know what the state is. They told you what the state is. They gave you the values of x, y, z, and w. And now you're going to go and you're going to measure both of these qubits and see what you're going to get. Well, you're going to either get 0, 0, or you're going to get 0, 1, or you're going to get 1, 0, or you're going to get 1, 1. Okay, boom. Let's say we did it. We got 0, 0. Now that other person does it again. They give you a new set of, or they re-prepare now this quantum memory in the same state, and you measure it again. Boom. Now this time you get 1 and 1. Now they re-prepare it, and then you measure it again. You get 0, 1. Now they do it again. They prepare it, reset it, and now you get 1, 0. So you see all four possibilities are present. What are the probabilities? Max Born worked out the probability formula. You take these numbers like x and you just square that number, and this gives you the probability. And I won't, of course, try to go into the details, but you'll see some analogies to this mathematics later when we talk about light polarization. You'll see kind of why the square makes sense for it. But this is just the mathematics, and it always works perfectly. Here's a poll question, which I call a non-poll question. So just think about this one. Okay, let's say we have a quantum memory cell, the green box, which has two qubits in it. And we prepare it in this superposition state. So remember, plus means superposition. So this state 0, 0 is in superposition with this state 1, 1. Now let's say you measure the qubit A. Let's say you do that and you obtain value 1. What do you think will be a measurement outcome of qubit B? I haven't told you the answer to this. You have to think about this. I can now reveal the answer, I think. Bingo, 1. Okay, why is that? It's because when you first measured the qubit A, you obtained 1. So what that does is it knocks out this possibility. You know the qubit is not revealed a value of 0, so this possibility goes away, and you're only left with this possibility. This is a combined possibility of A and B. A is 1, therefore B, if you measure it, has to be 1. So that's sometimes called collapse of the quantum state. Collapse just means by a measurement, you've eliminated one of the possibilities. And now you know something more about it. It's not that you've learned more about the state because you knew the state initially. You already knew what the state was to begin with, but you now know more about what are the measurement outcomes most likely to be. In this case, you know with 100% probability what the measurement outcome for the B switch is going to be. Okay, that's how collapse of the state works. So here's a poll question number 5. It's just reenacting the one we just did. So I'm going to let you just read this one, and I'll give you 20 or 30 seconds to answer.
And while we are taking time to do this, I just want to say that we do see all of your Q&A questions in there, but sometimes they don't really fit within lecture material perfectly. So during our break, we're going to make sure we answer all of the questions at once.
Okay, let's end that poll, Abby. Okay, so most people answered 1. Sorry, most people answered B, I guess. The observed outcome of A allows you to infer that B is in the state 1. That is correct. And the key point here is the difference between the word caused and the word inferred. So in that, I'll just discuss this. We're at the end of part 1 here. So this is a very important point that I want to emphasize before we take a 5-minute break. The point is that when you measure 1/2 of an entangled state, you're interacting with one of the particles, one of the qubits, which is in this case is some kind of a switch or electron spinning. You're interacting with that. The other one is off to the side. You're not touching it. You're not interacting with it. Yet you learn something about the other one. So that's what we mean infer. You gain information about the measurement outcomes of the other particle by measuring the first particle. Now, you can think that's either trivial, like a classical situation where you just had correlations. But it's not that trivial because entangled states are not the same as classical correlated states. But still, this dictum here applies. It's very important. Correlation does not imply causation. So in correlation, you could have a classical situation. For example, you have 2 balls, one red and one blue. You shake them up in a box. One person pulls out a ball and they see that it's red. Now they immediately know the other person's going to get blue, correct? That's a classical correlation. But notice that by the first person observing the color of the first ball, it doesn't cause the other ball to have any color. Even if the ball is many kilometers away from the first ball, it's a mere correlation. It's not a causation. If it were a causation, you could use that experiment to transmit information. Information transfer or communication means what you do here in my location affects something in a far distance. It might take some time, like if I put a smoke cloud up as a signal, it takes some time for a distant observer to be able to see that smoke cloud. It doesn't happen instantaneously. In that case, the information is being transmitted by the vision system, right? The second person is using light scattered from the smoke cloud. The light travels from the smoke cloud to their eye and they observe it. So there's a little time lag there. But in this case, we have quantum correlation. Yes, there are correlations, but there's no causation. And we know this because you can prove using quantum theory in its full mathematical form that if you had a causation effect, if my measurement here caused the other one to change its value, then I could use that as a communication system. But you can prove, if quantum theory is valid, that that's impossible. You cannot use this correlation to transmit information. It merely gives you more information about the state of the distant particle, but that doesn't affect the state of the other particle. So it's kind of mysterious. So I'll give you time to think about that. And I believe we're going to take a 5-minute break here.
Yes. So a few things. One, a couple of people pointed out that the last poll that showed up on Zoom didn't match the text on the screen. That was fully my bad. I think there was some mislabeling or miscommunication between the two of them. But either way, hopefully we all learned something good. And Mike, we do have a lot of questions building up. So I figured what might be better is if you care to hear any of the answers for these next 5 minutes, stick around and we'll answer them. And then if not, I think we should just spend the next few minutes going through them, if that's all right.
That sounds good. Everybody can take a 4-minute to 5-minute break now, or stay around and participate in the question and answer.
Yes. I will leave the recording going, so those who do need to step away, the discussion will continue on the recording.
Very good. Thank you.
Perfect. Thank you, Brianna. Okay, so our first one, Edward asked, could the expression with the ampersand and plus sign be explained in words again? Because there's a little confusion on that one.
Okay, so we first talk about the plus sign, and it translates to in superposition with. So if I have a single qubit or single quantum object, it can be in various states, like spinning clockwise or spinning counterclockwise, but it can also be in a superposition state, which means it has possibilities to be measured in one or the other. So it represents two possibilities at the same time. That's called superposition. The ampersand only applies when you have two quantum objects, like two qubits or two switches. Then we talk about the combined state. One example I like to give in class is, let's say you have a couple. The couple could be both short, or they could be both tall. They could be short and tall, or they could be tall and short. So when I talk about the state of the couple, I have to specify the state of this one and the other one. So now consider two people. If they were quantum people, I could have a single couple, two people, in a superposition state, but a superposition of combined states. So I could have both short, which means short and short, in superposition with, so plus sign, tall and tall. So that's the meaning of it.
Perfect. Okay. John asks, how does one know the state of something is indeterminate? Even with binary, one has to measure / know what the state is.
Right. So the difference is that in binary, when you have that refers to classical objects like light switches, we call those states definite states, because before you measure it, the switch is definitely either up or definitely down. Okay. It's a definite or definite. Determinate. Okay. But with quantum switch, it could be in a superposition state of up and down, and we call that I call that indeterminate. So even though you know the state, so this is a little bit, maybe I confuse the language. Sometimes I say you can know the state exactly, which would be like 0 + 1, 0 in superposition with 1. You can know that state definitely, you can know it completely, you can know it perfectly, but the measurement outcomes are still going to be indeterminate until you make the measurement.
Okay, wonderful. The next question is referring to the spinning top diagram.
Yep.
In this diagram, where we know 100% it is rotating around the 30-degree rotation axis after measurement, do we know what direction it is still rotating around the 0-degree axis, and is it still clockwise?
No.
All right, there we go. Okay, next question. What if we measure on the vertical axis again? Is it still clockwise?
I think that's the same as the previous question, and the answer is no.
Too. You're right.
Yeah,
I'm just reading them out loud.
You get probabilities. Yeah.
Perfect. Okay. Can you elaborate a little bit more as to why each measurement is not independent from previous measurements in the poll question? Says Aaron.
Why each measurement is not independent from the previous measurement? The measurements are independent. I'm not quite sure what the question is, but let me just say what I think is that each time you make a measurement, the system, you could say, decides or creates a particular outcome, and that actually resets the state to a new state, which you now know because you made the measurement and you saw the outcome. Now, given that new state that's been set, you can now predict with with probabilities the outcomes of any future measurement along any other axis using the Born's rule and the mathematics, which I haven't shown you. Okay.
Yeah, that's how I interpreted that question as well. But Aaron, if that's not correct, please ask a new one. We have another student asking, is there a reason we only consider 2 entangled states for each ion? Why not counterclockwise and clockwise and counterclockwise?
That's redundant, because if I just have one ion, there's only 2 possibilities. That's the meaning of qubit. The word bit means 2, like binary. And so a quantum bit has 2 possibilities. It depends on, of course, which axis you choose, but if you choose a given axis, it can only be spinning clockwise or counterclockwise around that given axis upon measurement. Okay.
Perfect. All right. Bob asked, does the order of measurement matter?
Yes, it does. The measurements if they're performed in a different order, you get a different result. And a very famous experiment, which I haven't shown, won't show, is if you have linear polarizers, maybe we'll explain this later. If you have 2 linear polarizers that are crossed, perpendicular, no light gets through. But if you stick a linear polarizer in between those 2 at 45 degrees, then light will get through the sequence. And if you change the order of those polarizers, you get different results. So that's a very good example. And quantum measurements are the same way.
Okay, and
probably
David,
move along pretty quickly here.
yes, and David asked why we're only choosing 0 and 1 when X, Y, Z, and W should be complex numbers.
That's 2 parts. They should be complex. Oh, the reason is because half of the people attending this course do not know what a complex number is, I would hope. And therefore, we simplified the examples to only consider real numbers.
Okay. Bob also asked that presumably the measurement process could either change the state or add new states, correct?
Could change the state or add new state. Well, again, for a given qubit, there's always only 2 possibilities relative to a given axis. And so the measurement process, yes, it does change the state, and it does, it could involve new states, yes.
Okay, and then let's see, we're getting new questions as we come in.
That's okay. Let's keep going. Ask more questions.
Yeah, well, I'm looking to see which ones.
Oh, Sicilian. I like that one. Why is it that the only possible states are 0, 0, and 1, 1? Is that an assumption we are making? Yes, that's an assumption we are making. In other words, I'm giving examples here, and I don't always want to give the most general example in my examples. The examples are meant to be, subsets or simplified cases.
Okay, our next question is, in your profession, have you ever seen confusion before regarding infer versus cause?
Well, yes, absolutely. Many people who are supposedly educated in quantum, although maybe not experts, like policy people or manager types, they'll say things like quantum entanglement allows instantaneous communication. And then the experts have to say, no, I'm sorry, that's not correct, because there's no causal effect. Therefore, you cannot communicate. You can only infer information about what the other person will observe when they make their measurement. So yes, many people have this misconception.
Okay, perfect. Next question, could you clarify the difference between quantum measurement and classical measurement?
Yes, a classical measurement means you are revealing a pre-existing value of some quantity, like 0 or 1. Quantum measurement does not mean that. There is no pre-existing value of the 0 and 1. The 2 possibilities are in superposition, and you are revealing the outcome of the measurement. You're not revealing anything about the pre-existing value of the thing.
Okay, perfect. Next question. What experiments or logic led us to using the convention of thinking about this as spin? If it's just an arbitrary characterization, then we could instead use vector, which might make more sense considering polarization states.
That's a very deep question, but it goes back to how you measure it. And the way you measure it is using magnetic fields. And it turns out that the measurement process behaves in a very similar way to what happens if you measure a magnet. If you take a magnet and make a top out of it and spin it, you produce a classical spin, and you can measure that with magnetic fields. It turns out when you measure the single electron with magnetic fields, the behavior is analogous or is very similar to the classical spin. Therefore, we simply use the word spin. We name it spin, but it doesn't really mean anything is spinning. You're quite right. Nothing is spinning.
Okay, perfect. Follow-up question to one you answered earlier. Is it not also redundant to say counterclockwise and counterclockwise, or 1 and 1?
No, because there we're talking about two different objects.
Okay.
If I say 1 and 1, I have two different atoms, and I'm saying they're both spinning clockwise, or I'm saying they're both spinning counterclockwise. That's not the same as if I have just one spin and I say it's in a superposition of spinning clockwise and counterclockwise.
Okay. Someone asked, there was a classical correlation example is that one ball is red and the other ball will be blue. What is the quantum correlation example to this?
I will show that in the later slides. So
Okay.
let's move on here.
Perfect.
Okay, thanks everybody. That 5-minute break was 10 minutes because you had so many great questions. I really appreciate that.
Yes. And hopefully we'll keep answering them as we continue on.
Yes, correct. And of course, if there are any questions, Abby, that you feel should be answered in real time, please let me know. But at this point, we are going to transition over to Abby Gookin, presenting the lecture material. So I will advance the slides on your command, Abby.
Perfect. Thank you so much, Mike. Hello, everyone. My name is Abby Gookin. I'm a systems and quantum engineering student at the University of Arizona. And I'm going to be lecturing this second part of the course, which focuses on encoding and transmitting quantum information. So we can continue on. So just an overview of this part, we're going to be talking about kind of classical communication systems and how we're transferring all of that knowledge over to quantum communication systems, as well as how we encode information within qubits, and some examples to really delve into what a quantum network is like. So first, focusing on communication systems. So classically, what a communication system is, we have a message source and a message destination. So we start with a message source, which is usually transmitted through symbols, then goes through a transmitter, then to be directed to a receiver, and then the message is considered received. And usually throughout all of these different steps, we have noise sources, which makes it a little difficult to adequately and accurately relay messages. And so information theory classically answers these types of questions. So how much information can be carried by a certain number of symbols, how exactly we carry that information. And then looking to quantum communication systems, we ask what new capabilities are made possible using this quantum state encoding. So first, what is a quantum communication network? You know, at the meat and the bones of it all, a quantum communication network is a network of channels and nodes that transmits or shares quantum information. So a lot of what we know about classical networks can be transmitted to talk about using quantum information and transferring quantum information. So then what is quantum information? It's information encoded in quantum states of physical objects. So kind of what Mike was just talking about in the previous section. And so when we talk about quantum information theory, we're asking how we can transform entanglement between nearby qubits to entanglement between far separated qubits. And that's really what the Center for Quantum Networks works to achieve. We're trying to achieve the nearby qubits and transferring that information to far separated qubits. And so in this next section, we're going to be looking at the equations we see below. So the state equation, where A and B are of states 0, and in superposition with A and B of being in states 1. And we're going to look at a couple different examples of this, but really what we're going to be focusing on are entangled qubits separated by arbitrarily long distances. So next slide, please. And this is where we're really going to get into space-based quantum communication. So this is where you're going to see a lot of the more unique applications we're going to talk about later on. So distributing entangled photons across very large distances and utilizing this for various modes of communication. Next slide. Perfect. So we're going to pull up poll question number 7. Let me get this ready. All right, so we have our state equation above that gives qubits A and B to be of state 0 in superposition with qubits A and B being of state 1. So at 12 o'clock noon, Alicia observed its qubit A to have a value of 0. So at what time does Alicia then know the state of qubit B without observing it? All right, we're going to do about 5 more seconds for this one. I'm going to end the poll and share our results. So the majority of people said immediately, which, if we reveal the correct answer, is the correct one. We also had a lot of people saying C, which is understandable as well. So really, we're going to be focusing on these state equations for the next couple of poll questions. So if we know Alicia has, or if Alicia observes qubit A to have a value 0, then we know we're going to be looking at that first set of parentheses within our state equation. We know that qubit A is 0, so that's the only part we want to focus on, and we're going to cross out the rest of it. So then if qubit A is 0, we also know that qubit B has to be 0 given this state equation. And this is just something Alicia is able to know. She's just able to infer it from the state equation without needing to make any additional measurements. So therefore, the answer is she's immediately able to know the state of qubit B without observing it.
I guess I could interject that Alicia has
please.
to, Alicia has to know beforehand that the state is the one given at the top.
Yes.
If she knows that, then she has a lot of power she can use to predict the other one.
Yeah, and it's that same premise that we're going to be using throughout the next couple of poll questions. So that's a really important idea to grasp. Next slide, please. So this is our follow-up question, which is not a poll question, but just something to think about. So using that same starting condition. So at 12 o'clock noon, Alicia observes qubit A to have a value of 0. So what time does Bob know the state of qubit B without observing it? Excuse me. So we'll give a few seconds to think of this one. All right, and if Mike, you want to reveal the answer here. This one, it's not a trick question. It's exactly what you think it is. Bob will never know the state of qubit B. Alicia tells him what she observed. So Bob is pretty much in the dark here. He doesn't know really anything until Alice decides to give him some information. So since he does not observe anything, he does not know the state of qubit B. Next slide, please. So really, this is the equation we're going to be looking at, this state equation. And so at 12 o'clock noon, just to recap the last couple of polls, Alicia observes qubit A to have a value of 0. So Alice then knows the state of qubit B immediately, but Bob does not. However, Alicia can phone Bob and tell him, and there's a time lag limited by the speed of information, so the speed of light, which is what a lot of you said for the last poll question. But whatever Alicia observes does in no way affect, or whatever Alicia observes or does to qubit A in no way affects qubit B, and that's a really important idea to grasp. But ultimately, what we need to know here, and a really large limiting factor of quantum networks that people don't necessarily understand, is that there is no faster than light communication allowed within a quantum network. So that is a hard and fast boundary we have within quantum networks, is that faster than light communication is not possible. Next slide, please. So now we focus on qubits and how exactly we're encoding qubit information within them. So we're going to look at 2 different types. We have stationary qubits and flying qubits. So stationary qubits are usually used for storing the quantum information, and flying qubits are used for transmitting quantum information. And so within those stationary qubits, we're going to focus on electron spin states, which is what Mike had just discussed, and also the states of superconductor currents. And then for flying qubits, we're going to talk about the polarization states, the time of arrival, or time-bin states, as a lot of people refer to them, photon frequency, and the photon beam path as well. So now, looking at how we encode information into single photons or qubits. So encoding in polarization. So polarization can be oriented in various directions perpendicular to the direction of light. You might be familiar with this from physics way back when, or physics that you're taking now. But really, we're just going to be talking about polarization of light. So here we have the vertical polarization, so up and down, and that's also denoted by the 1 that we've been using. And then also 0 represents horizontal polarization, so kind of going in and out between you and me. So the 0, 1 are the logical values, and a single photon encodes what we call a qubit. And so over on the right-hand side, you can see a polarizing beam splitter, so a calcite crystal. This is a lot of times what we use within the labs, where we're able to actually split photons based on their polarization states. And this is how we use this is kind of how we use it within a real life example to detect different polarization states. And we also have time taggers and all those different things and single photon detectors. So this is how we measure the qubits. Next slide, please. So now we take that classical idea of polarization and we introduce a superposition of this. So using the same idea of superposition we've been using previously, we have V plus H, so vertical polarization and superposition with horizontal polarization, and this is diagonal. Now, if we do V minus H, this is going to be anti-diagonal, and these are two different superposition states we have within qubits. And so we see Mike referring to those above, where H plus V kind of goes to the top right, and negative H plus V goes to the bottom right. So remember that plus means in superposition with, and if you're not necessarily as familiar with polarization states, you can also just go back to using those zeros and ones we were talking about previously. And so it's important to know that the polarization can be oriented in any direction perpendicular to the direction of travel. And so we also see those coefficients X and Y that kind of talk about various degrees. And it's really important because the second either those X's or Y's change, really everything's going to be flipped on its head. So one thing we're going to talk about, if we can go to the next slide, excuse me, is the fragility of these states. So these are really fragile ways to encode information because even a simple phase change can change the state drastically. So here are two different examples. If we just make Y into a negative Y, if we just flip that phase for a split second, suddenly the state really changes pretty drastically. And so this is something we have to keep in mind quite a lot. And a lot of these phase changes will lead to something we call decoherence, which leads to a lot of errors we see within the labs and even within theory. So fragility and decoherence is something that we absolutely have to consider when we talk about quantum networks. Next slide, please. So now we talk about the entangled polarization states of two photons. So with one photon, we had the 0 and the 1, the horizontal and the vertical. But now we're talking about two photons, A and B. And so we're going to talk about these example states, 0 and 0, and superposition with 1 and 1, what we saw before. But now we're going to be talking about it in terms of polarization. So horizontal and horizontal in superposition with vertical and vertical. And sometimes we'll also use these with arrows. It's all meaning the same thing. It's just a different notation. If you're a visual learner or if you like seeing the letters or the numbers, all of these are similar things. Just use whichever one you're more comfortable with. So next slide. All right, poll question 8. Let's pull this one up. So relaunching poll number 8. So we have two photons in the entangled state. So the state equation is A and B are horizontal and vertically polarized in superposition with A and B being vertical and horizontally polarized. So opposites for both A and B. The A photon goes to Alice and the B photon goes to Bob. Bob measures his photon and obtains a horizontal polarization. What will Alice observe if she measures her photon using a polarizer that separates H and V? All right, we're gonna give about 10 more seconds for this one. All right, 5 seconds. I'm going to end the poll and show the results. All right, the majority of people said vertical, which is the correct answer, if Mike wants to show that on the screen. And the way that we're able to know that is if Bob measures his photon and obtains H, we're going to be looking at the second half of that state equation, right? We can cross out the first part, we can ignore the first part, and all we know is we need to focus on that second set of parentheses. And so if B is measured to be horizontal, then we know that A is going to be measured as vertically polarized. And so even if it goes through a polarizer that separates H and B, excuse me, it's still going to come out to be vertically polarized. And that is why we get B as our final answer. We're going to be stop sharing. All right, next slide, please. All right, the other way that we can encode information into single photons is encoding in location. And so this one we're not going to go into in as much detail, but all you need to know is that photons follow a wave path, right? And so sometimes they can be determined on the upper path and sometimes they can be determined or measured on the lower path. And so that upper path is going to be 0 and the lower path is going to be 1. And so this is also easier to imagine as information being encoded just by the location in space. So we can just determine if a photon is here or there, and the detector will tell us exactly where it is. And that's going to be how we determine those zeros and ones. So next slide, please. And we can also use this kind of same idea for encoding in time of arrival. So rather than being here or there, we can also refer to it as now or later. And so using this classical light pulse and an oscilloscope and a time tagger, we can do a bunch of different things to determine whether or not a photon is going to be early or late. So in this example, this is just a classical example of one single photon. And so this one is telling us that it's early, right? The light pulse, the voltage jump we're seeing is early. And then we can also see it later in time as well. So this early is referred to as 0. And if we go to the next slide, we can see it as being later in time.
Let me just interrupt here that the classical example is not a single photon. You just misspoke on that. It's
my apologies.
It's a light pulse containing thousands of photons.
Yes, there we go. Sorry about that.
Okay.
Yes, and then this one is showing the exact same example, but just later in time. So that oscilloscope is measuring the voltage, and the time tagger is just telling us it was late, and this is referred to as 1. So next slide.
I'm going to toggle back to the other one. See, there's
Yes.
a 0, there's a 1, there's a 0, there's a 1, 0, 1.
Perfect. So now we have a superposition of those things. And so using a quantum light pulse, we get 0 in superposition with 1, or early in superposition with late. And so that time tagger is going to tell us 50% early, 50% late, or it could be 0 minus 1. So it's going to be the same probabilities, but the minus state is distinct from the plus state. So again, those phase changes are really going to change the information that we're able to encode. And so encoding the information in quantum light pulses is pretty fragile as well. All right, so encoding in time of arrival, this is just another example of what we saw. So early or late, or intensity of power being earlier in time versus later in time. And then on the right-hand side, you can also see the electric field. So we can see exactly that voltage measured, again, early or late. And so at the bottom, we see the superposition. So 0 plus 1, those are going to be 2 in-phase times. So you can see the crest of both waveforms right at the top, right at the peak of that wave. And then also 0 minus 1. So it's going to be a phase change. That second one is going to be flipped out of phase. And so you can really see the trough being at the very bottom. So again, we're just talking about this idea of fragility. So a simple phase change can and will change the state dramatically, which is why we really need to keep that in mind. And that's a really important feature of quantum networks that we try and refer to at all times. And so just as a summary page, so we recall that one photon can either be 0 or 1, early or late. And then an entangled state, so the state example or the state equation is going to be early, early, in superposition with late, late, or early, late in superposition with late, early. Really, any kind of example you prefer. It's all talking about the same thing. So, next slide, please.
And just again, we could also have early and late, and we could also have late and early. There's 4 possibilities.
Yes.
I'm only showing 2 of them just as a simple example.
Yep. All right. One other thing that we really need to discuss are that no copy of qubit states are allowed. So how to transmit a qubit state from one place to a place further away. We ask maybe, could this be a quantum telephone? But it's important to note you cannot make a copy of a state without destroying the state of the original object. So a quantum communication network must transmit the state of the physical system, although it may do so by state teleportation, which we'll talk about later, which is kind of a complex way of us trying to imitate a copying of those qubit states, because we cannot copy them without destroying the state of the original object. If we can go to the next slide. So a useful tool to do this is we use a joint measurement tool. So now we're going to be talking about coins. This is just a single coin. So we have coin 1 and coin 2, and they're going to go into a joint measurement tool. And a joint measurement tool just gives information about the pair, but not the full information or details about each member. So the joint measurement tool is just going to tell us whether they're the same or whether they're different. It can't tell us.
Let me interrupt. You just misspoke. You said we have a single coin, but we actually have 2 coins here.
Yes, sorry, I meant a single coin on each side. That was my apology. So a single coin on each side, they both go into the joint measurement tool, and the joint measurement tells us whether they're the same. It can't say whether they're both heads or both tails. It'll just say whether they're the same or different. So in this example, we're seeing that they're the same. And if we go to the next slide, we will see that they are different. Oh, this one's still the same. My apologies. So this is the same example outcome number 1. So they're the same, but it can't say 0 or 1 or 1. It just says they're the same. And so now looking at the state equations below, we have the two state prepping sources. So we have state 0 and 1, and state 0 in superposition with state 1. Again, we're not quite sure which one. We just know information about the pair, but not the full information about each member. If we can go to the next slide. Oh, this is example outcome number 2. Same slide, just talking about that they're different. So 0 or 1 or 1 and 0, but it can't say which.
Here's case
And then this one,
yeah. Here's
yep,
case
this one's
2.
the same.
Different. Okay.
Perfect. Okay, so now we talk about entanglement swapping. So how do we use that joint measurement tool to try and start with 2 separate entangled states and swap the entanglement of those? So this is called entanglement swapping. So we have entangled state of A and B with the state equation below, and we have the entangled state of C and D with the state equation below. So if we forward a little bit, perfect. Now we take that joint measurement of the 2 of them. So B and C both go into the joint measurement and we're given an outcome. That outcome is going to say whether B and C are the same or different. And we're going to kind of use that quote unquote hint or that clue that the joint measurement gives us to determine the states of A and D without ever really interacting with the 2 of them. So we can go to the next slide. So prime example, we have A, B, and C, D initially shown in the states below. So 0 and 1 in superposition with 1 and 0 for both A, B, and C, D. So the joint measurement yields that B and C are the same. The outcome is that they are the same. They're either both 0 or both 1, or both 0 in superposition with both being 1. So then what is the state then created for A and D? And there are 2 possible cases for this. So possible cases that B and C are both 1, and that's in superposition with the idea that B and C are both of state 0. So we have this 2 state equations labeled above. So if B and C are both 1, we know that the right-hand side of that first equation is gonzo, right? B in this equation is not equal to 1, so that's not quite right. And then in the next equation, the first part is gonzo. Cross it out. It doesn't mean anything. We don't use it. Then in superposition with B and C being 0, we're going to do the same thing. And we're left with the final state of 0 for A and D, and superposition with 1 for A and D. So those are our 2 options. That is the final state. And that's our final state example using this primary example. So next slide, and we're going to have a poll question with a very similar example. Okay, so now poll question 9. Launching this poll now. So A, B, and C, D are initially in the state as shown. So the joint measurement yields that B and C are different. What is the state then created for A and D? We're going to give you a lot more time for this one. So take your time and use the same example we saw on the last slide. All right, we do have a question requesting that we slow down a little bit so we can read the equations. I'll be sure to do that. That was my bad.
We could go back if you want.
I think we'll do this one because we have the next slide. We'll just take some more time in the next one.
Okay.
All right, we still only have about 50%, so we're going to give 10 more seconds. All right, I'm going to end this one here and show the results. All right, question mark. So the majority of people said A, but this one is definitely the most mathematically complex poll question we're going to see in the entire course. We're going to go through this one a little bit more in the next slide. So the joint measurement yields that B and C are different. So one is of state 0 and one is of state 1, but we're not quite sure which is which. But all we know is that we need to find the state then created for A and D. So the two possible cases are that B is 0 and C is 1, but that's also in superposition with the possibility that B is 1 and C is 0. So looking at the very first one, we're using those two state equations we see at the bottom of the screen. So we're just rewriting them. So the first equation is for AB and the second equation is for CD. Now, if B is 0, we know that the first part has to be crossed out. That can't be a possibility because it says that B is 1 in this first one. So we cross that one out. And then in the second part of the equation, we know that C has to be 1. So again, we cross out that first part because that's not possible. This state equation says that C is 0, and that's not what we're given in this case. So we cross those two out and we're just left with the second halves of both equations. Now this is in superposition with the values of B being state 1 and C being of state 0. And so again, we do the same process. So we have the two equations and we know that the latter half is not going to be a possibility because it says that B is 0, and that's not what we're given in the case. And in the second equation, we know that C cannot be 1 because that's not what we're given in this case. So we cross that one out as well. And so then we are then left with two equations that were given in the final state. We combine them. And so the final state of this equation is that A is of state 1, D is of state 0, in superposition with A being of state 0 and D being of state 1. Now we're not quite sure which it is because we haven't done any measurements on it, but all we know is that the poll question 9, the answer is indeed A. And this one again is the most mathematically complex problem we're going to see for this, this entire course. You will all get copies of this recording as well as lecture notes, so feel free to go through that and delve into more time, give some more time for yourself to go through it. And if you still have questions, feel free to reach out to either of us at the end of this course. And now, if we go to the next slide, I'm going to toss it back off to Mike to go through quantum state teleportation.
Thank you very much, Abby. That was quite a bit of challenging material for people who are brand new to the subject, but we wanted to show you at least one actual detailed calculation. And what you just saw was actually the workings of quantum theory. It's actually no more complicated than that. It's mathematically. It's pretty confusing conceptually or philosophically because we don't, understand intuitively what superposition means from a deep classical point of view. But we can certainly manipulate the equations and then we get exactly the right predictions for the probabilities of measurement outcomes. So now the question is, if we understand all that, how can we use this to do something useful? Now, in a quantum internet, which we don't have yet, it might be very useful for a person up here in this location to have an entangled state of A and B, and you want to transmit the B part of it down to this other person and to a qubit called C. So let's just start with a simpler problem. Let's just say that the person here has a single qubit and it's in state B, and they want to transfer that qubit state down to here onto a different qubit, C. Well, how can we do this? This is called state teleportation. The reason it's called teleportation is because we do this without sending this particle, B, across the internet. It stays back here in this lab. The only thing that's teleported is the state of qubit B onto the state of qubit C. So it doesn't work with macroscopic objects like human beings, but it does work with small objects like single electrons or single photons. Okay, so here's how we do it. Let's say that Professor Xavier has a state and he has prepared that state using whatever methods, either lasers and microwaves, or maybe for photons you would use polarizers to prepare a state, and the state is X weighted onto the 0 qubit state in superposition with the Y weighted value on the 1 qubit state. Now remember, if Professor Xavier just measures that particle, he will find value 0 with probability equal to x squared, or he'll find the value 1 with probability equal to y squared. That's what we talked about earlier, the Born rule. But let's say that wouldn't be useful, because if the professor measures that particle initially, he only gets very little information. He finds 1 or 0. That doesn't tell him what the state is. So we can't just measure it and send that information to Bob, because there's no way that the professor can determine the values of x and y for a single particle. Therefore, if the professor wants to transmit or teleport that state to Bob, here's what they can do. They have to use an entangled state, which I abbreviated here as ES for entangled state, of 2 qubits. So in this machine here, there are 2 qubits, which could be spins, or it's probably going to be photons, actually, because we're going to move them around here. So we have these 2 photons in state, this entangled state 0 and 1 in superposition with, oops, that's a typo, isn't it? Sorry, that's a mistake. You see why that's a mistake? Those are the same thing. Sorry about that. It should be 0 and 1 in superposition with 1 and 0. We'll correct this before we distribute the slides. Okay, now the B particle is sent to Bob across an optical fiber. And so it takes some time, a few seconds to get to Bob. The A photon is sent over here to Alice, who has a certain role to play. What Alice does is takes the particle in state X from the professor Xavier and combines it with the particle A in a joint measurement, which Abby just explained how it works. And that gives an outcome. Now, remember, as Abby said, measuring the joint measurement does not tell you the state of either particle A or the particle X, but it does tell you some information. And I'm not going to go through the mathematics of this one, although it's not very complicated. But what Alice can do with this outcome information is she can now telephone over to Bob and send a classical message. And she can tell Bob what the outcome of her joint measurement was. So that's limited information. But it turns out if Bob just sits there by himself, there's no way he can know what the state of X is. But if he has 1/2 of an entangled photon pair, he has B, he takes the information that he receives on the phone call from Alice, he operates a very simple device which does a controlled transformation on this particle B without knowing the state of the particle B. And magically, this now particle B is now in the same state X that the original particle was in at the professor's side. That's state teleportation, because the particle X was never sent across a large distance to Bob. It just stayed here and was stuck into the joint measurement, which is locally. There's a long distance between Alice and Bob, you see. Okay, so Alice never knows the state. In fact, the professor also never needs to know the state to do this procedure. But if the professor wants to verify that the internet is working correctly, the professor will prepare the state many times. We'll do the experiment and ask Bob later, well, what did you get? Bob will report back what he got, and then he'll say, oh, yes, the internet is working correctly. But the real point is that this state can be transmitted from the left-hand side to the right-hand side over a long distance without anybody ever knowing the state. You can verify it later, but you don't know it in between. Now, one point, as Abby mentioned, is that this classical message cannot travel faster than the speed of light. So C is the speed of light, V is the speed of the signal. And so you cannot have faster than light communication or faster than light teleportation. Okay, notice that the particle X no longer exists. It was sacrificed. It went into the joint measurement. And remember from earlier, we said when you make a quantum measurement, you change the state of that particle. So this X particle is still hanging around here, but it's no longer in the original state because it was measured. So that particle is sacrificed, and the state of that particle is now reproduced over here on Bob's side. So this is consistent with the fact that you cannot copy a state. Remember, Abby said there's no photocopy machine for a quantum state. And this is consistent with that, because if there were, then what Professor X could do is a trick. He could just make many copies of his particle state on many particles. Then he could determine what that state was by measuring all those particles in some clever way. And then he could just telephone Bob and say, oh, okay, make that state, without ever having entanglement. But this is impossible, because there's no way for the professor to copy the state. So the best he can do is sacrifice the state into a joint measurement, and then the state appears on Bob's side. That is quantum teleportation. Now, in principle, you can teleport more complicated objects than a single photon or a single electron. In principle, you could teleport the state of an entire atom, or possibly the state of a molecule. But it turns out that if you wanted to teleport the state of like an amoeba or a virus, it turns out that's too much information. And it's impractical to do so for many, many reasons. So we'll never be able to teleport the state of a person from one place to another. Okay, now going back to what I said earlier, if the original particle X is actually initially in some entangled state, so for example, we could have, again, this is the same typo here. Oh, sorry about that. This should be 0 and 1 in superposition with 1 and 0. That's an example of an entangled state we could have prepared back here at the source, ES. Now, let's say we want to do an experiment where we teleport the X state over to Bob, but we leave the Y particle sitting over here. We can do that just by the same exact procedure. So we teleport it over, and now the particle X has been sacrificed. And now, after Bob makes the controlled transformation on his photon B, which is up here now, is entangled with particle Y in exactly the same way that particle Y was entangled with particle X at the beginning. So you can teleport half of an entangled state using the same procedure. And all the mathematics of this is pretty straightforward. And if anybody really wants to know how the equations work, just contact Abby and myself later, and we'll send you some equations. Okay. So now, turns out that there's a synchronization problem, because photons travel at the speed of light, and they arrive when they arrive. You can't slow them down, so they arrive when you need them. So this photon might arrive at Bob too early to be of use. He doesn't know what controlled transformation to put on the photon because it arrived already, and he hasn't yet received any information about the joint measurement. So he'd like to be able to store that photon, and we do that what's called a quantum memory. So we store this photon B in a quantum memory, which is a device that captures a photon into a material. It absorbs the photon into an atom or another material in a way that its state is preserved. I'll tell you later how to do that, but for right now, just assume this is possible. And then we could push a button and we can release the particle A and release particle B whenever you want. So then once that state is prepared and transmitted, this solves the synchronization problem, because you can release them at any time you want. So now it doesn't really matter how I produced and when I produced the quantum entanglement between the two memories, because I can release those particles anytime I want later. So then we can do the same procedure with entangled resource that's pre-shared and pre-stored. That's a very important step. And it turns out that one of the biggest technical challenges in all of quantum network research is how to build these quantum memories. We don't actually have really well-functioning quantum memories at the present time. We do have them, but they can't store for a very long time, and they typically also can introduce errors and mistakes. So we need to perfect the quantum memories. Well, here's an example of such a thing. People are trying to do this experiment, but nobody has done it yet. NASA would actually like to get funding to set up this experiment with a satellite, but they don't have the funding yet to do that. I see my typo persists here. This should be 0 and 1 plus 1 and 0. And the satellite will have a source that emits a pair of photons down to the Earth, and they'll be stored in the quantum memories. And then whenever they feel like using them, the professor and Alice can do the joint measurement. Alice can send say an email or a text over to Bob, telling him the result of the joint measurement, and then Bob can then he can release his photon, put that photon through a unitary, which, forget the word unitary, I just mean a known controlled transformation. And then that particle is in state X, which is the same one that the professor generated. Okay, that's how it works. Now, why do this in space instead of through optical fibers? It turns out that in the short term, we'll probably be using satellites in space to do long distance quantum communication, for example, between two continents. And that's because optical fibers are not perfect. And if you send a photon through an optical fiber, it tends to be lost or absorbed, doesn't go very far. Whereas coming down from space, if you do things correctly, you can transmit over a very long distance and still have a chance to receive the photon at the ground station. And here's some examples of applications that you could use it for. Here's some more examples of applications, which I don't have time to go into in detail, but you can research on the internet and learn all about these cool applications. All right. So we'll take a 5-minute break now, and we'll come back and start talking about what's called Bell state measurements, which is the research that received the Nobel Prize a few months ago. See you in 5 minutes. And feel free to put questions in the chat now if you like.
Yes, and Mike, we are building up a lot of questions. So I've been answering the ones I can via typing, but if you want to go through and pick some that you would like to answer at the start of our next section, that would probably be a good idea.
Okay, so you're in the Q&A, right?
Yes.
Okay, so let's see. We starting out with, I'll just read them and pick out the ones I think are maybe the most useful.
Go for it. Yeah, we've got about 50 of them building up. We've got a lot of wonderful questions.
Oh, okay, I apologize for skipping some of the more general questions, like if they're more philosophical questions, and I hope you can just read many articles on the internet about these philosophical questions, like what is reality, what's a thing, and so on. These are very tough questions to answer because we actually don't know the answers to them. Let's see. Yes, again, there's Bob Lance asked, I'm puzzled about the height examples, because in the height examples, I said they could be short and short, or tall and tall, or short and tall, and tall and short. That's an example of the most general possible entangled state. But another example of entangled state would just be the following: short and short in superposition with tall and tall. I can prepare that state, not for people, of course, but for electrons. So we're just giving different examples. It doesn't mean I have to always include all 4 possibilities when I give an example. Just like if I have a ball and I say, here's an example of the ball, red. I don't have to say it could be orange or green. I just have to say my example is red. Okay, let's see. Let's keep reading here. Now here's a really tough one. What is the difference between probabilistic correlation and entanglement? Now, I mentioned that, but I'll just try to restate it because it's really not obvious. Probabilistic correlation occurs in classical physics. What's the probability that people in the population are going to be tall and also have red hair? That's a classical probabilistic correlation. It's not the same as entanglement, because with entanglement, well, for example, another classical example, I have 2 people. What's the probability that they both have red hair? Okay, that's a classical correlation. But if I have 2 electrons and they're in an entangled state, and I say, if I measure them both on the vertical axis, what's the probability that they'll both have clockwise spin? That's a very different thing than the classical case, because first of all, I can change the measurement axis for either electron. I can measure one on the vertical axis and one on the horizontal axis. So there's no counterpart of that in the case of the 2 people with different hair colors. And furthermore, the way that the mathematics works is very different. It allows me to do things like quantum teleportation of a state and so on. So entanglement in quantum physics is very different. And it's hard to say in words why it's different, except by giving examples. But the underlying reason they're different is that for quantum states, there's no underlying value that's predetermined before you measure it. The measurement outcome is created upon the measurement. That's not true for the color of hair of a person, right? The hair has a particular color before you measure it. So that's the underlying reason. Okay, let's see. How do you do the measurement? Well, it depends on the system. If you have photons, you use polarizing crystals or polarizing filters, as Abby mentioned. If you have electrons, you use magnets and you send the electrons through some magnets and you see which way they're deflected, left or right. So it really depends on the system. And for superconducting qubits, you measure the current and so on. There's all different ways to do it depending on the example. And we're given the discussion in a more general context. We just call 0 and 1 the two states, and we don't talk about always how to measure them. Okay. So here's another question about causality. Marco Ruffini says, if the measurement on A modifies the state of B, so its measurement will be 100%, is that not the same as causality? And the answer is no, because it is true that you change the state, but it's not really a change. It's more like you're filtering. It's like you're selecting, because remember, the particle B was already in a superposition state. It already had both possibilities, 0 and 1. So by making the measurement on the other particle, you're not changing the state of B, but you're learning more information about the combined state. You're learning more information about the state of B, but you're not physically causing it to flip between 0 and 1, because it was never definitely in state 0 or 1 to begin with. It was in a superposition. So it's quite different, but I agree, it's puzzling. That's why you need to think very carefully about that. And it leads to the fact that there's no faster than light communication. That's a very important physics fact. And we know that's true. Okay, keep on going here. Yeah, there's a question about spin. Is that the same as angular momentum? It's quite different. If you have a physical top, a metal top, it's spinning, that has angular momentum, as we learn in physics. A spinning electron is different. It's actually a point particle. So you can't really talk about a point particle spinning, right? There's no physical extent to spin. The only reason we call it spin is because it obeys much of the same mathematics and much of the same measurement procedures as a physical spinning. So it's not an actual rotation. And here's a question from Gert Grammel. Does every measurement affect the state? Answer is no. But the only exception is if the state is already known to be a particular state, say clockwise in the vertical direction, and you measure in the vertical direction, then you get the same, you get the result without changing the state. But any other case, if you measure on a different axis and you get some result, that will change the state. So yes, measurement does change the state in general, but there's special cases where it does not change the state. Okay. I'm going to skip that one. Oh, yes. Bob Lance asks, how does Alicia know the state equation? She doesn't always know it, but in the examples we're giving, we assume she knows it. Now, how does she know it? Because she prepared that state in the beginning. So she prepared it according to a known procedure, which has been previously verified to produce always that state. The other possibility is that Professor X prepares the state into a state that's known. He provides the particle to Alicia, and he simply tells Alicia, I prepared this state. So now she knows what the state is. Okay. Let's see. We're moving on. Time is running out here. So let's see. These are all great questions. I really love the fact that you're all asking questions. Yeah, we can have all different possibilities. People are still asking, can it be 0 and 1 and 0 and 0? Yes, That's another possibility. Travis was asking that question. You could have 1 and 0 and 0 and 1. Remember, there's 4 possibilities, and you can add all 4 possibilities together. And I put coefficients in front, X, Y, Z, W. So I did show a state that has all 4 possibilities. But then later, we were just focusing on simple examples where the particles were prepared in a particular state with only 2 of the possibilities included. And that's usually the most useful thing to do for things like teleportation. Yeah, so measuring 1/2 of an entangled state doesn't force or cause the other particle to be in a certain state, but it knocks out or filters out certain of the possibilities, leaving only other possibilities, as Abby explained quite nicely. Polarization, the question is, are polarization based on transverse or longitudinal wave propagation? The answer is transverse. So the electric field in the light wave oscillates transversely to the direction in which the wave is traveling. Okay. Oh yeah, somebody asked, are there alternatives to photonic flying qubits like phonons? And the answer is yes. If I tap on my computer, I'm transmitting sound waves to my ear through the air. And in theory, you can use vibrations like that, which are called phonons. And if you do it carefully, you can operate those at the quantum level. So look up quantum phonons entanglement on the internet. You can find that. Okay, I think we're going to move on, and maybe we'll be able to circle back to some of these questions later, but these are great questions, and if we have time at the end of the whole course, people can stay on longer and we can answer more questions. So with that, I will close the chat box and move on to part 3. Thank you. Okay, so now we're to the third part, Bell state measurements. Well, Bell is named after John Bell, a famous person. And we'll talk about photons again, quantum measurements again, correlations again, and then we'll talk about the Bell test experiments, which uses all the previous concepts. So we're going to be reviewing some of the material we've already covered, because I believe that sometimes when you see something for the second time, it makes more sense. So here's a review. Abby showed that if we have, in the picture, we have a laser, and it's emitting light of some polarization, which, as we just said, is a transverse oscillation. You see how I drew the pictures? It's oscillating. This little red line is the electric field. It oscillates in a direction up or down relative to the direction of propagation, which is from the laser to the detector. Now, that oscillation can be in a vertical sense or a horizontal sense. And this crystal has a property that it splits the light beam into 2 parts depending on the polarization. You can buy the calcite crystal in a gem store for about $1. And if you lay it down on a piece of paper with a writing on it, in sunlight, you'll actually see duplicate copies of the letters in the writing. And that's because you're seeing the light from the sun has both polarizations, vertical and horizontal, and the crystal is separating those into the 2 different parts. That's also how 3D glasses work in a movie theater. The 2 eyes are looking at opposite polarizations. Okay, so we talked about that. We talked about the most general state of polarization is the electric field can oscillate at any angle relative to the V and H directions. And notice in this picture, the light beam is traveling into the screen. From where you're sitting, looking at the screen, the light's traveling from your eye into the screen, and the light and the electric field is oscillating transversely with some angle relative to the H and the V axes. Okay. So now Abby also said that depolarization or diagonal can be thought of as a special combination of H and V. Here's how we think about that. Think about, it looks like a compass, but it's a directional indicator. So if I tell you to travel northeast from the origin to a place northeast, you could get there by first going north and then going east. That's the same as going from the origin to the northeast point. Okay, So you see that the northeast direction is a sum, or actually we call it superposition of vertical direction and horizontal direction. So here's a little picture that summarizes that. And here's a polarization example. So you see that the diagonal depolarization, in other words, if the thing is oscillating along this axis, that's the superposition of oscillating in the V direction and the H direction. Now, if you still can't visualize that, I'm going to switch over here to a little program that I adopted. And Abby, tell me if this is not working. I'm going to switch over to my other program here. And you can see what I have is if I start the animation down here, okay, time is running, but nothing's happening on my little point here because the field amplitudes are 0. So now what I'm going to do is I'm going to increase the amplitude of the horizontal field oscillation. So now it's oscillating back and forth. Now, again, the light is traveling from your eye through the screen, and the electric field is oscillating in the transverse plane horizontally in this example. So you see the H component is oscillating in time. This axis is supposed to be time on the horizontal and amplitude on the vertical. And down here, you see the other one is still at 0. The V component is 0. Now, what if I reset this one to 0? Should be able to 0. Reset that to 0. And now set the other one to non-zero. Now I have the vertical electric field amplitude oscillating positive and negative. And the horizontal component is still 0 when plotted versus time. You can actually see that little line moving along. That's showing what the time is. Okay, but now if I have them both non-zero, watch this. I can make it do this. If I have a lot of V and a little bit of H, I can make it do that. And if I have equal, I can have more, or I can have more. So now the H and V are the same amplitude, and I'm getting a beautiful anti-diagonal oscillation. The dotted arrow is the actual electric field, and it's simply the summation of the two electric fields shown in red and green. Now, as Abby said, if I cause a phase shift here, like this, by clicking this button, I now have a diagonal polarization oscillation. And you see what that means is over here, the H component and the V component are synchronized. They're oscillating the same. They're getting positive, max, 0, positive, negative in synchrony. But if I now desynchronize them by a certain amount, I can now make them slightly out of phase. And now they're oscillating. When they add up together, I get the anti-diagonal. So see, the amplitudes are the same. The energy in both are the same. It's just that the phase has been changed, and that changes the state completely. And if this phase change is uncontrolled, this can lead to errors in the quantum communications. Okay, now I'm going to switch back to this and just click through those examples showing the in-phase oscillation and showing the out-of-phase oscillation. Okay. Now, visualize a polarizer. Think about polarized sunglasses. If you wear polarized sunglasses, then one of the polarizations of light is blocked. That's the one I show here that's perpendicular to these vertical slots. And the other one that's parallel to the slots gets transmitted through the polarizer. Okay, in this case. If I have a horizontal polarizer, or if I take my sunglasses and rotate them by 90 degrees, it's going to block the other one. Now it blocks the vertical and it transmits the horizontal. Okay, this is if I have a polarization that's at 45 degrees. It's composed of both of them, but I can filter one or the other out. So here's a poll question. Put that one up, Abby. What is the polarization of transmitted light after the vertical polarizer? Okay, so I have, let's say I have sunlight, and it contains all polarizations or some mixture of both polarizations. And I put it through a vertical polarizer. What is the polarization of this light that comes through? Please answer on that one. Okay, we'll stop there and review and show the results of the poll. Good. Yep, you got the idea there. So exactly, just the way I drew the polarizer slots, it only lets that guy through and it blocks the other one. Very nice. So that's V. Okay, what about this one? Show that poll question. I'll let you read it. Okay, do we have enough answers there, Abby, to show the results?
I think we do.
Okay, let's see that. No light comes through. Oh, that's exactly correct. Okay, perfect. No light comes through this case. Now, previously I was talking about laser light or sunlight. That contains trillions of photons every second. Actually, trillions of trillions of trillions of photons every second. Now, here, let's say we have a single photon. Now, I haven't actually told you how to make a single photon, have I? One way to do it is just to put some very strong filters in front of your laser, very dark glass, and then only one photon can leak through at a time. You get a very low flux of photons and they arrive one at a time. Another way to make a single photon is to take a single atom, like remember those ions that were trapped? Single ion, use a laser to excite that ion to a high energy state, and then just sit back and wait. That single ion will emit light, but it only emits one photon because when it drops down to its lowest energy state, it can no longer emit a photon. So that's another very nice way to generate one photon. Let's say you did that and you produced, and you knew you were producing vertically polarized light. These three arrows don't mean three photons, sorry. There's only one photon coming, goes through this vertical polarizer. Now we talk about the probability. So let's show there's no poll question here. So just think about that, right? Okay, what is the probability there? Well, it's going to be 100% because this polarizer transmits always the vertical one. So it's a probability, but it's kind of trivial because it's 100%. Now let's consider a single photon, the same photon. And we know it goes through the first polarizer with 100%. Now the question is, what's the probability that this photon is going to get all the way through this sequence of two polarizers? So think about that for 5 seconds. I don't think I've actually told you how to solve this question exactly. So don't worry if you don't think you know how to solve it exactly. I'm going to show you how to solve it. Okay. So the answer is 50%. So you can just kind of imagine, well, it's halfway between 100% and 0, right? Because this polarizer is rotated halfway between 0 angle and 90-degree angle. And that's more or less the correct answer. So it's partial transmission probability. Now, if the photon does not transmit through the polarizer, what happens? It either gets reflected from the polarizer in some unknown location or it gets absorbed into the material of the polarizer, and you can never get it back out. It's gone. However, I should have asked you this question, what the state of the photon is if it gets through. If it doesn't get through, it's a moot question, but if it gets through, we know that that photon now has been changed from a vertical polarized photon into a diagonal polarized photon because it has decomposed the vertical polarization into a sum of diagonal and anti-diagonal, and only the diagonal part or the amplitude of the diagonal part has transmitted through. But once it gets through, now you know there's a photon there. If you put a detector here, you detect it. And so now it's been reconstructed as a diagonal photon when it started out as a vertical photon. So that's a good proof that measurement actually changes the state. Okay, now let's consider this one. What do you think the probability is now that it's going to get all the way through all three of these filters. Okay, there's no poll question, so I'll just go on and reveal it. Well, the first polarizer has a 50% probability to transmit through, and the second one also has a 50% probability. So you multiply those together, you get 25%. And now the photon has been transformed back into a vertical photon, if it gets through. If it doesn't get through, there's a moot question, it's gone. So that's the sense in which quantum measurement is like a filter. It doesn't, well, here it does change the state, but if there's an entanglement going on, it only changes the state of the local particle that you're measuring. It doesn't change the state of the far away particle. That's kind of an interesting point. Okay, now let's look at a little bit of mathematical representation of the same thing. Let's now just go to an abstract geometry picture. Forget about polarization. We can think of the polarization direction as a quantum state. It's an arrow or a vector. And here's an arbitrarily drawn arrow with some arbitrary angle. The length of it is always equal to 1, because that means that we have a photon with 100% certainty. We know we have a photon. Okay. The symbol is called psi, which is the name that Schrodinger gave to it. So fine, we can put this is called a state arrow or state vector. You can point it any direction you want, and that direction defines the mathematical representation of the state. It's not a photon, it's a description of the state of the photon. And remember, state is not a description of the actual pre-existing value. It's only a statement that you know mathematically can be used to predict probabilities upon any future measurement using any measurement axis that you choose. That's a long sentence. There we go. It's not a property. It's a description of the photon. Okay, going back to Max Born's rule, remember we said that you just take the amplitude and you square it. So in this case, I'm going to call the amplitude A, but it's not the amplitude of the full vector, which is equal to 1. If I square that, I get 1, which tells me I have a photon. But if I have this state, this red arrow state, and I have this polarizer, which is not parallel to the state, what I do is I project this arrow onto the axis of the polarizer, and I get a length which I can measure to be A. You could actually measure this with a ruler if you had the proper scale. If this scale is 1 inch, then you can measure this in inches. You get a number like 1/3 of an inch, you square it, and if A is 1/3, you square it, you get a 1/9. So it'd tell you that the probability that this photon state would pass through this polarizer is equal to 1/9, or 1 out of 9 tries. If you do it 9 times with the same state, on average, one of them will successfully transmit to the polarizer. The other 8 trials will lead to the photon being lost and absorbed in the polarizer. That's the Born rule. The other alternative is I could rotate my polarizer 90 degrees from this angle to this angle, and now I just have the complementary projected axis. And if I project it onto this other one, I get B. Now, if you remember your geometry, we have Pythagorean's rule. Pythagorean rule says a squared plus b squared equals c squared, but c is equal to 1, so that's 1 squared. Now, isn't that interesting? This is how Born figured out the rule. He said, look, the probability that it's going to transmit through one axis or the other axis has to equal 1. Because if I use a calcite crystal instead of a polarizer, I know the photon's going to go left or right. So the two probabilities have to add up to 1. Well, a squared plus b squared is 1. So he said, well, a squared looks like a probability. And it turns out that's exactly correct. And earlier we had x, y, w, and z. And if you square x, x squared is a probability that that one is going to be observed. Y squared is a probability that the other one's going to be observed. And so you're working in higher dimensions, but the mathematics still works just fine. Here we only have 2 possibilities, so you can visualize the Pythagorean theorem very nicely. And here's just a summary of everything we've talked about. These are the little pictures that Abby showed of polarization. If we call that a 0-bit value, a 0 qubit, and then V polarization is a 1 qubit. Here I represent these on my little graph paper, V and H. And now here shows why the probability is 50% if you go through a 45-degree polarizer. If the state is this one, depolarized, this is diagonal. This over here is anti-diagonal, but down here is diagonal. Now we know from Pythagorean theorem that I can construct this vector, this arrow, by adding 0.71 of a V arrow together with 0.71 of an H arrow, and they add up perfectly to a diagonal. Well, but if I take each of these 0.71s and square it, I get 0.5. That's 50%. And you can apply that to any different angle using this graph paper trick that you like. Okay, moving along quickly. For example, if you have on the graph paper, you have X and Y. For example, X could be some number less than 1, and Y could be some other number less than 1. But remember, the sum of the squares has to add to 1. And if you now send that photon through a calcite crystal polarizer, it's going to, if it's V, it comes out down here, H comes out here. But remember, it's not preordained or predetermined which way it's going to come out. And when it comes out, it has a new polarization because the state was in this tilted angle. If it comes out on the upper path, now it's a horizontal. So it looks like this up here. If it comes out on the vertical path, it looks like this, it's vertical. So the measurement process has changed the state again. And the probabilities are given by the square of these amplitudes called X and Y. Okay, that was a very quick course in quantum mathematics. Here's a question. If you have paper or just think about the answer, let's consider this sequence of experiments. I start out with a single photon that I produce by an atom emitting it, and I prepared that such that it emits a polar photon from this source towards this analyzer with a D orientation angle. The vector or the quantum state is D oriented 45 degrees in a transverse plane. Now it goes to a HV analyzer, so it can either go up here to H or it can go down here to V. And then if it goes H, it goes through this AD analyzer, which is just the same kind of crystal rotated by 45 degrees, which has the property that if it's D, if it comes out D, it goes this way. If it comes out A, it goes this way. And likewise, the V, if it goes this way, it could come out here. So there are actually 4 places that this photon could arrive. You could have 4 detectors and detect where it arrives. So what do you think are the probabilities that it will arrive here, 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 or here? Okay, that's probably long enough to think about if you know the answer or not. Well, the answers are equal. They're all 25%. That's because it had a 50% probability to go vertical and horizontal in the first choice, and a 50% probability to go D or A in the second choice. So that works out. And I could rotate these crystals to any angles and use the Born rule with the Pythagorean theorem rule to get all these probabilities. It's a lot of fun, actually. But now we get to the real point. The real point wasn't to learn the mathematics. The point was to try to predict some very interesting experiments, which earned a Nobel Prize. So these are non-trivial issues, which I hope to walk you through. So let's consider how to describe this set of experiments. Notice I could have more crystals. I could have a 100 sequence of crystals, many thousands of crystals. And I could try to predict in all kind of different orientations of crystals. And I could try to predict what are the probabilities of coming out in all these different locations. Well, how would I do that? Well, 2 ways to do it. One is with classical physics. And people were asking earlier in the chat, well, how do you know that nature, that photons and electrons don't have predetermined properties? I've said that a few times, right? I said that the value of the property is created upon the measurement. It was not predetermined. It's not just a matter of determining or measuring which one it was, because that's an ill-posed question. It wasn't either. It didn't have a value. It only had a quantum state description. So how do we know this? Well, the classical model would force you to have the following theory, which turns out to be wrong. You would say, I know that this photon has built inside of it an instruction set, many, many instructions, which is like maps, like a Google Maps, that it knows that it's supposed to follow a certain trajectory through this large sequence of polarizers and come out here, okay? And maybe the next photon has a different instruction. It follows a different path and comes out, say, here. And every photon has built inside of it a classical set of instructions telling it where to go. Well, that's possible, right? The universe could be built that way. And here's just a list of 5 different photons with their different sequence of map instructions. Well, maybe that's the way the universe works, but it turns out, no, it doesn't work that way. How do we know that? For one thing, I could add any number of crystals here. So the photon, as small as it is, would have to have an infinitely large set of instructions. That's a little bit odd. Okay, but more to the point is this one, that if you just look at single photon events, you can not really answer this question, because philosophically, you cannot rule out the possibility that these instruction sets exist. That would be called realism. Now, the Bell inequality is a way to test this idea. And the question is, does classical common sense theory describe the world correctly, as I just tried to describe it? Well, we know that you can, the popular media talks about spooky correlations. And in fact, Einstein started that language because he just thought it was weird. It didn't seem like common sense. And Einstein was a very common sense scientist. He liked things to be concrete. And even though he was one of the originators of quantum mechanics, he didn't believe that entanglement was a real thing. It turned out that he was wrong about that. So we talked about the differences between correlations in classical theory and quantum theory. In classical theory, it refers to any statistical relationships involving dependence of one thing on another thing, okay? Well, we need two photons to look at correlations. It doesn't do to just look at one photon and measure it many times. So we have a source that emits photons in pairs. Now, how can we do that? Consider a single atom that's excited to a very high energy state. Its electron is in a very large orbit with high energy. Now, the electron could drop down to an intermediate state orbit and emit a photon, and then it could immediately drop down to another lower state, maybe the lowest possible state, and emit a second photon. So one excited atom, in that case, can emit a pair of photons. And if you're lucky, the 2 photons go in opposite directions, and you can use calcite crystals to analyze the polarization of both of the photons. And now I can look at correlations. Now the question is, are the correlations classical or are they quantum? And here's how you would do it. You would have some sequence of measurements. Okay, now to really describe this in classical probability theory, you would have to have a very lengthy list of possible correlations, almost an infinite set. You know, in other words, if this photon made a detection at the very upper point here, what's the probability that this other photon is going to land on any one of these 8 detectors? Well, but I can rotate these crystals any way I want, even rotate them to continuous angles. So you need some very complicated set of instructions, but maybe it's possible. Turns out it's not. We can prove it's not. How? By doing experiments. And this is why people got the Nobel Prize earlier this year, for experiments that they did 50 and 40 and 30 years ago. It took that long for the world to catch up with the importance of it. And the reason that the world did, and the Nobel Committee did catch up with it, is because of the advent of quantum information theory and quantum information technology, such as quantum computers, quantum sensors, and quantum communication networks. Once it became a practical impact, people realized, oh, this is not just philosophy. This is real physics, and entanglement is a real thing, and it enables you to do real operations that you could not do without entanglement. Okay, so let's say we give these assumptions. These are what would be called common sense assumptions that most people, if you just grab somebody on the street and told them about physics, they would probably think these are reasonable assumptions. In fact, I think they're reasonable. I'm quite shocked that these are not reasonable. So the first assumption would be that we're going to build our classical model upon is we assume that after the photons leave the source, their inherent properties or predetermined properties or instructions, they exist and they don't change. So the two photons go off on their own different travels. Each one has a set of instructions that it's going to follow. Now, those instructions could have been built initially so there's a correlation. You know, they both grab their instructions. They're not identical, but they grab them from a prepared set of instructions that have correlations built in them. That's fine. And the next pair of photons might grab a different set of instructions that are correlated. And you could try to describe some of the correlations that are observed in the photon measurements by appealing to this idea of pre-prepared correlation instructions. That's called realism, because the instructions exist under this assumption. They really exist. Okay, now the other one is causal effects cannot travel faster than light. We call that locality, or I call it causal locality. We believe that's true because of relativity. Nothing's instantaneous across a large distance. Now, the third one is that Bob and Alice, who are they? Bob is the person on one side who makes measurements. After setting up his polarizer crystal angles any way that he wants to. And Alice is another person on the other side that sets up their polarization measurement devices with arbitrary angles. And the assumption is that they are able to make independent choices about what measurement each will make on each of their observed photons. We call this free will. But if the settings are made by computers instead of by people, then free will doesn't make sense. So we call it measurement independence. The computers on the two sides are assumed to be not communicating. So if we make these three assumptions, one can prove, and I'll prove it to you in a second, there's a limit on the possible types of outcomes of certain well-designed experiments. This limit is called the Bell inequality. Okay, we can do experiments to test this as well. So now I'm going to build up this by an example of two dancers. This is in my little book that I mentioned earlier. So of course, dancers are classical, so they don't correspond to quantum correlations, but it's easy to describe the situation first using classical objects. So we have these two dancers. They can each put their arm up or they could put their arm down. You really only look at one side, say the left arm. Now, their behavior, when they do two different dances in two different locations, they could be uncorrelated, they could just be randomly moving their arms up and down, or they could have a very particular dance they're doing, but they're not correlated. That would be the typical situation, right? Now, how do we check for correlation mathematically? What we do is we observe the arms and the arm positions of the two dancers many times, and then we calculate something. So on the first observation, I call it a run or a trial, Alice is watching her dancer. And if the arm is up, Alice puts down a +1. If the arm is down, Alice puts a -1. Now Bob is observing their dancer in a different room and puts down a plus or -1. So on the first run, they see plus and minus, as I've shown in the picture here. Now the product of those two numbers is -1, right? On the second run or trial, they see -1 plus 1. So the product is -1, etc. In this case, they both see -1. So the product is +1. Now what they do is they make thousands of these trials. Then they come together later and they compare their two vertical lists of measurements. And they look at all these products. They average the products. In this case, you would get roughly 0 because there's equal numbers of +1s and -1s. That shows if they're uncorrelated, then this correlation product, which is the average of the product of Alice result and Bob's result, would be 0. Okay. However, if the dancers are perfectly correlated, let's say they both memorize the same exact dance and they dance them at exactly the same speed, and then Alice and Bob made the measurements at exactly synchronized times, then they would always observe the same results. See, plus, 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 plus. Here's a case where they observe minus, minus. But now notice all the products are positive, because when one is negative, they're both negative. So the product is always positive. So all the products are positive in this example. Now the correlation is 1 because the average of that is 1. So if they see later when they compare their lists of data, they compute the products, they average it. If they see equals to 1 or something near 1, they say, aha, I know that those dances were correlated. So that's how you do the experiment with the classical dancers. Now, let's say we need to make it more complicated to do the Bell test. So let's say that they could observe either the leg or they could observe the arm. And again, you get +1 or -1 for leg up or down, and arm +1 or -1 for arm up or down. Now, these two dancers perform in two different halls or buildings, and Alice is observing this dancer and Bob's observing this dancer. And again, they make synchronized measurements. They have a clock and they start exactly at the same time. And every 1 second, they record the position of the dancer's arms and legs. And then later they come together and compare the results. So here's a chart that I made up showing some examples. In fact, what I've shown here is a complete systematic list of all possible combinations. This is not a set of trial runs. This is just a table showing all possible combinations. So they could observe 1, 1, 1, 1, or they could observe, say down here, 1, -1, -1, -1, or they could observe all -1s, the different combinations. Now notice that if I take any one of these combinations, which is a horizontal row of 4 numbers, I compute the 4 products of arm times leg, leg times arm, leg times leg. In this case, I get all +1s. Now, I can create this table of all those combinations. Now, here's a curious thing. John Bell, who was a very smart physicist, he looked at this table and he said, well, what kind of sense can I make of this table? He considered all kinds of possibilities, and he realized that the most important quantity that I could produce from these 4 numbers up here is the following: this number plus this number plus this number minus the 4th one. Now, I call it curious because to you and me, it's not obvious why John Bell picked this combination. It turns out that this is the most revealing one, so that when you do the quantum experiments, you can distinguish between classical reality and what I'll call quantum reality. That's a very smart thing. That's why we call this a Bell test, after John Bell. So there's many ways you could process this data, but this is the very clever way to do it. So for example, here we have 1 + 1 + 1 - 1. That's equal to 2. Here we have 1 - 1 + 1 - -1. That's equal to 2. Here we have -1 + 1 - 1 - 1. That's equal to -2. So notice that every possible combination of observations that Alice and Bob could observe, they always produce +2 or -2. They never produce a number greater than 2. That's the key point, okay? So I'll give you a spoiler. When you do the quantum experiment with electrons, this quantity 2 turns out to be greater than 2, which looks kind of impossible, right? And that proves that the world really is quantum, not classical. So moving along with the example here. There's a subtlety though. And it turns out that in some experiments, such as those with electrons, only one of the 2 possible measurement types can actually be done on each single object. So for example, with dancers, you could clearly record both the arm position and the leg position simultaneously. And Bob could do the same thing. But in certain quantum experiments, you can only record one or the other. Just a spoiler here. For example, if you measure a spin of an electron, you can choose to measure it on the vertical axis, or you could choose to measure it on the horizontal axis. But for a given electron, you cannot do both. Because remember, the first measurement changes the state. So the second measurement is then pointless. So the classical story then goes, well, what if Alice and Bob can only see either the leg or the arm on a given instant? And the story I make up is that the room is very dark and there's a stroboscope that's either pointing to the arm or the leg. And so when Alice looks, she can only see the arm or the leg at any given time. And it randomly switches between the arm and the leg. So what you have to do is look at these kind of trials and block out every other possibility. So in each possibility, Alice only sees the arm or the leg, and she records that. And Bob sees only the arm or the leg and records that. And they take those two numbers and multiply them together. But notice there's only now one number out of all these four possibilities that they can record for a single trial. Now they repeat the trial 1,000 times, boom, boom, boom. And for each trial, they get one number, either this one or this one or this one or this one, you know. Now they can't calculate Q for, which is this quantity here, for a given trial. But what they can do is a trick. They can calculate the average of Q. They can average all these numbers down vertically, the A times A. They can also average all these results and then average all these results. And they get these four numbers down here, which are averages. And now they can take those numbers and combine them according to Bell's formula, this one plus this one plus this one minus this one. And they get a number. Now, the proof is that in classical physics, this average can never be greater than 2, because all the underlying numbers in the Q column would never be greater than 2. So you couldn't average them and get something greater than Q, 2. But in the quantum theory, it turns out you do. That's pretty cool. I'm going to go a little bit speed up here. I think you're probably getting a little bit sleepy for all these details. You can look at this later. It's possible that you can rig the system. It's like rigging an election, which you've all heard a lot about lately. It's possible that the universe could rig the election in some unknown way so that only certain conspiracy measurements were obtained, and you could get a measurement scheme like that. And in this example, you could actually get Q equals to 4, even with classical physics. So what that means is when you do the quantum experiments, you have to make sure somehow that the universe is not rigging your experiment and making this Q greater than 2 and trying to fool you. So, but we know how to do that. So I'll explain that. In other words, you have to prove that there's no conspiracy between the measurements on Alice's side and the measurements on Bob's side that are just conspiring in some unknown way to make Q greater than 2, even though the classical probability theory could still be valid. So you need to rule that out. So this is what John Bell proved. He said for any data set, W, X, Y, Z, you can form this quantity, the product plus the product plus a product minus this last product. And you can prove mathematically, which I just proved actually, you can check it later, that the average of this Q can never exceed 2 unless there's rigging or conspiracies. That's the theorem. That's called Bell's theorem, Bell's inequality. And it's true. I just proved it. Check me later. But under the assumptions of realism, causal locality, and fair sampling or measurement independence, you can prove that that's the true statement. So therefore, if you do an experiment and you find the average of Q is greater than 2, you know that at least one of these assumptions is wrong. And philosophers get very nervous when you start talking about this. And physicists say, well, that's just the way it is. Don't worry about it. So now I'm going to show the experiments with photons. I've chosen 2 characters. Alice is going to be represented by Alicia Keys, a famous musician, and Bob by Bob Dylan. So there's a source here, which is an atom which emits a pair of photons, and then you repeat it. The atom emits another pair of photons, and you do this thousands of times, and you make the measurements. So for a poll question, let's show that poll question. For a given single photon, this is a warm-up question. Can you measure whether it is V or H, and also measure whether that single photon is D or A? Okay, let's send a poll there. Okay, so most people said no, the first polarizer changes its state. And I guess I kind of gave away the answer there when I said earlier exactly that. Interestingly, though, some people said yes for classical light and no for quantum light. I'm going to reveal my answer. So C is partly true. It depends on how you think about it. Because it's true that for a laser beam, you could measure both D and A. You could just simply split the laser beam on a partial reflector of some sort, and then measure HV on one of the beams and measure D and A on the other beam. However, for a single photon, you cannot do that. That's the quantum aspect of the problem. If you have a single photon, you try to split it on a piece of glass, it either goes through the glass or it reflects off the glass. It can't do both. So no matter where the photon goes, then you can still just put it through one type of analyzer or the other type of analyzer, but not both. And if you do it sequentially, it doesn't tell you anything because the first one changes the state. Okay, good. So let's move on then. That means that Alice and Bob can only choose one quantity to measure on a given photon. This is where the choice comes in, the free will. Alice can choose to set her polarizer this way, or she could rotate her polarizer to a DA analyzer and measure whether it comes out D or A, but she can't do both. And Bob likewise. Bob has a free choice for setting the crystal angle to analyze it. Okay. Now, think about, I just revealed the answer by accident. So moving on, do you expect correlations between Bob and Alice's measurements to be correlated? Well, the answer is it depends on how this source is behaving. And the experimenter has to build the source in a very particular way to create correlations. In general, there might not be correlations. If you just have like the sun, emits lots of photons. And if you pick up one photon here, another photon there, they're not going to be correlated. But if you do this trick I mentioned earlier, where you excite one atom, and then it emits one photon, and then it emits another photon going to its lowest energy state, it turns out that the photon polarizations now are correlated. In fact, they are entangled if you design the experiment correctly. So now we can use that entangled state to distinguish between this idea of classical correlations and the idea of quantum entanglement. So let's first do the case where light comes from the sun. So the two photons going away from each other are uncorrelated. So the way it's done is that Alice gets a measurement. This detector gets we call it a click. It's like a Geiger counter. So this detector registers a detection and clicks. And if that's so, then Alice says, well, my value W, she calls it W for some reason, is equal to -1. But if this lower detector clicks, Alice says W equals +1. Now, Bob has a variable he calls Y for no particular reason. He calls it Y, and he says, well, if this one clicks, Y is -1. Notice the opposite from here. No, it's the same. If the upper one clicks, it's -1. If the bottom one clicks, it's +1. So they do this experiment many times. And they observe that there's no correlation. The correlation is close to 0 if they do it thousands of times and average the results. So that verifies, because there's simply no correlation between here and here. So you can get some +1s and some -1s over here when you do the product. Over here, the product. Okay. However, if John Bell tells us exactly how to prepare an atom so that it emits correlated and entangled photons, now they're going to get a different result. They're going to see correlation, but more than that, they can prove that entanglement is a real physical thing. So here's an example, just some random example that I made up, no particular reason for it. But what they observe here in this particular Bell state, we call the state that's produced by the atom, we call it the Bell state. And if you produce a really good Bell state and make these measurements, you find out that the average of the product of W and Y equals -1. That says that they're very well correlated. In fact, this case we call it anti-correlated, which means that whenever Alice sees +1, Bob sees -1. When Alice sees -1, Bob sees +1. They're always opposite. So that's called a Bell state. It gives you a perfect anti-correlation. Well, there's nothing quantum about that, right? You could have a classical system where you have two balls and the red ball and the blue ball always go in opposite directions. So the measurement outcomes would be opposite, even though they're random. So this by itself doesn't prove entanglement. Let's move on now. Here's what I call the magic trick. This is the one that proves entanglement. And I don't have time to go through the mathematics for you, but the mathematics is not so complicated. So you have the Bell state, the same one I just mentioned, and Alice measures it either in the HV orientation, where she rotates her calcite crystal 45 degrees and measures whether it's D or A. She can't do both, right, for a given photon. Now, Bob does the same thing, but he uses two different angles. One is 22.5 degrees, rotated crystal. The other one is 67.5 degrees. And he calls those two variables Y prime and Z prime. So in any given trial, Alice chooses a crystal orientation, and she records, if she has a HV orientation, she calls it W, and she gets a ±1. If she has a 45-degree orientation of her analyzer, she calls the outcome result X, which can be ±1. And Bob does the same thing for Y prime and Z prime. So I know this is a lot to follow, but if you reread through these lectures later, it actually is pretty simple, and you can reconstruct it. So Alice has these two possible things she can measure, W or X, and Bob has two things he can measure, Y prime or Z prime. That's just how this experiment is designed. You don't have to do it this way, but John Bell proved this is the best possible experiment you could do. And so that's what people have done. So you might think that the classical Bell inequality should hold, namely the average of Q, this quantity up here, measured by Alice and Bob, could not be greater than 2. Well, aha. Here's the experiment that was done in Paris by Alain Aspect and previously done by John Clauser. These are two of the individuals who received the Nobel Prize. But you can see it was done a long time ago. It's amazing that it took so long to get the prize. So here's our atom source, emits a photon this way. Here's the polarizing crystal. Here's our two detectors. They can rotate these crystals any way they want, analyze. Here's a computer that computes the coincidence of the photons. And here's just some made up example I gave for the results. You have a million trials, you average them together, and aha, you find out that the experiment shows that the average of Q is equal to 2.8. I pause because that's actually a very shocking result if you believe in common sense, if you believe in reality and all those other assumptions. So classical physics prediction fails. I mean, that's not a big surprise. We know that classical physics is not correct everywhere, but this is a stronger statement than that. This is saying not only Newtonian physics fails, but our entire intuitive conception of what the world should be like for most people fails. And what it fails are what we call inherent properties or instruction sets, which you could also call realism, and also these other assumptions about measurement independence and so on. I'm going to discuss that here. So now we go to the conspiracies. Remember I said it's possible that classical logic and probability theory could be correct, and classical physics could be correct if there were some mysterious conspiracies rigging the whole system that we don't know about. We just haven't discovered them yet. So let's try to do experiments to rule out those we call loopholes. The first one, maybe they're an unknown phenomenon that can send information between Alice's and Bob's setups, allowing a hidden coordination unknown to physics. How do we prevent this? By closing this loophole. We separate the two labs by a large distance, so large that it would take a long time for light to travel between one and the other, because light travels at 1 foot per nanosecond. And then we switch the measurement settings. Alice and Bob both switch their measurement settings after the photons have departed from the source, but before the photons arrive at the detectors. And that completely eliminates the possibility of this kind of a unknown conspiracy between the two sides. And there's some hidden back channel that the universe is sending hidden messages between the labs. That's not possible if you believe in relativity and you believe that no signal could travel faster than the speed of light. Okay, what about this one? Maybe the detectors are conspiring. I showed those detectors, but I never said what they were. But maybe in reality, they have a limited detection efficiency, which means that sometimes a photon hits a detector and it fails to click. Typically 80%. Okay. If you had that situation, then the detectors could maybe communicate with each other in some way or in some predetermined way and conspire to rig the results so that Q is greater than 2, even though the classical physics model is still valid. But you can eliminate this loophole by using detectors with 100% detection efficiency, which people have done. Well, third one, maybe the experimenters or their computer's choice of measurement settings were being controlled by some external agent. So the two people on the two sides are being controlled by mind control by some nefarious agent to try to confuse them. Well, the way you can get rid of this setting, this loophole, is to switch the measurement angles, the polarizer angle choices randomly. And this is a very tricky one because people could still be controlled and they think they're doing random decisions, but they're not if they're being mind controlled. Well, computers, same problem. You could program computers to do independent things, but maybe they're really correlated. Well, most of that is eliminated already by having the fact that light travels no faster than the speed of light. So by having the labs very far apart, like many kilometers, you could eliminate the possibility of instantaneous coordination. But what you cannot eliminate is a possibility that the entire universe is deterministic. Namely, everything is programmed from the Big Bang onward. And so there's no such thing as free will. There's no such thing as random polarization choices and so on. Well, that gets into philosophy. It's actually very hard to eliminate this one. But we move on, right? Because now the question is not about philosophy and determinism and free will. The question is about, can we build technology that's based on entanglement? And does this experiment prove entanglement? Okay, so really quickly, this common sense person here, which I found on this website, would say, obviously, realism, local causality, and measurement independent exist. That's just common sense. Everybody knows that common sense is better than some crazy scientist telling me about some abstract mathematical theory. I just want to believe common sense. Well, you've heard the expression, some of you heard the expression, hold my beer. This guy says, I did the experiment. So strictly speaking, these experiments show that the combination of realism, causality, and measurement independence cannot exist. And common sense does not always hold sway. It fails sometimes. So moving on, we've learned a lot. What we've learned is that quantum theory predicts something called entanglement. And it turns out that the quantum theory predicts exactly the results of the experiment. Remember I said that Q is equal to 2.8? Quantum theory predicts, very simply, that Q is 2.8. So we know that there's a lot of evidence that entanglement is a real phenomenon, and we know that quantum theory correctly predicts that phenomenon very well and describes it very well. So given that, we can move on. And we can do quantum technology using this newfound physics. So we'll take a 5-minute break, answer a few questions, and then we'll come back. We have many questions here in the Q&A.
Yeah,
I'll pull those up.
Quite a few questions up in the chat.
Yeah. Are these new questions?
Well, so
yeah.
some of them are old, but I think what you do is if you scroll all the way down to the bottom, you can see all the most recent questions and answer those.
Yeah, I think it automatically came up. I'm on a question by Shruchi.
Oh, perfect.
It says, where is this time of arrival encoding useful? Yes, so it's useful in cases where, remember, Abby talked about the dephasing, decoherence, the fact that a very small phase change can completely destroy a state, can change the state. So for example, polarization. Polarization can be disrupted if it travels through an optical fiber. However, so that's bad. However, if you use this time of arrival encoding, the two parts of the state have the same polarization. So you're not subject to a small polarization change because there's only one polarization. So you don't care about that. And in an optical fiber, the phase between the two arriving time parts is not disrupted. That's a technical physics thing, but it turns out that it's more robust against dephasing if you use time encoding instead of polarization encoding. Okay, let's see. And I think the next question is similar. So now just to comment back about the vector states for a single photon. So for a laser, you actually have in reality an electric field oscillating transversely. And you can state that it's oscillating in a certain way, horizontal or diagonal or vertical, et cetera, or any angle in between. For a single photon, you don't have that. You only have the quantum state. So we don't say the electric field is oscillating. We simply say the quantum state is oriented in a certain direction on the piece of graph paper. It's not oriented in real space like optical polarization. It's only oriented mathematically on a piece of graph paper. But it turns out the mathematics is the same between the quantum photon state and the classical laser polarization. The only difference is that for a quantum single photon, the state tells us probabilities. That's all it tells us, but that's enough. That's all we can get. And then there's, let's see, moving along here. I don't know if you can all scroll, but I'm scrolling. All right, how to create superposition between different photon locations. Okay, so here's one way you can do it. I have a single photon, it's traveling through space, through my lab. Now I have a piece of glass that can transmit the photon with 50% probability or can reflect the photon with 50% probability. Now you might think that the photon either transmits or the photon reflects, but that's not true. The photon actually goes into a superposition state of both positions, reflected path and non-reflected path. It's a true quantum superposition. And you can prove that by doing other kind of experiments, which I won't tell you about now. So that's another example of the difference between quantum and classical. Okay, now people are asking more about the early late. So they're asking to measure if it's early or late, would it need a reference clock? Absolutely, yes. You need to measure early or late relative to a known time. And so you need to synchronize the photon source with the receiver. And it might be very far away. This is a major problem. So as the satellite goes overhead, it can be emitting pairs of photons that are time encoded. And then on the ground, you have to receive those and know if it's early or late. But that requires lots of synchronization and also requires accounting for the fact that the satellite is moving across the sky. So you have to know a lot, and that's a big technical challenge. So there's always pros and cons of different methods of encoding information on single photons. Okay. Yes, how does an avalanche detector determine if the photon is early or late? So given that you know relative to your clock, the answer is that the avalanche detector can amplify the photon. It gets a very little bit of energy in the detector, and then there's an electronic amplifier that amplifies it to a very large signal. And then a computer can simply have a clock in it, and it can record when that voltage pulse comes into the computer and records an event relative to the computer clock. Okay, now somebody says, is a joint measurement like an XOR operation? So for those who don't know an XOR, that's called exclusive OR, and that's used in conventional computer architecture or logic. The answer to the question is no. An XOR operation is not an operation, it's a measurement, first of all. An exclusive OR measurement is measuring the state of a single bit. That's different than a joint measurement, which Abby explained is for the purpose of measuring the relationship between the state of two different bits. For example, are the two bits in the same, do they have the same value, or do the two bits have different values, opposite values? So joint measurement always refers to a, joint means together, right? So combined measurement, whereas the XOR operation is for a single qubit. Okay. In general, measurements always change the state. Let's see. Yeah, so Scott Packard asks, does the distance limitation, 1,000 kilometers, extend to free space or only optical fibers? Optical fibers is the answer. We know that if you put a photon into an optical fiber, then it's definitely lost by 100 kilometers. In free space, it's a little different because if the satellite emits a photon from the satellite, you know that photon doesn't stay into a tight beam. Any light beam spreads out by diffraction, no way to stop that. And so by the time that light beam gets to the ground station, the light beam might be, 20 meters across, whereas your telescope might only be 1 meter. So you still have a lower probability to detect that photon in that telescope because it overfilled the aperture of the telescope. However, that loss, it only gets worse by the square of the distance traveled, whereas the loss in a fiber gets worse by the exponential of the distance traveled. For in practice, there's a very big difference, and therefore free space usually wins out over very large distances. Thank you for pointing out typos to us. We'll fix those. Okay. Okay, the question is, what information is Alice really transmitting? What job are we actually trying to do? So at the very beginning of this lecture, I gave a list of all kinds of operations that could be carried out using quantum technology. In this class here, we don't have time to discuss any of those. So what I have to say is that we're not transmitting information that a human would be interested in. Like if I send you an email, that's classical information, you would be interested in that. But if I send you 20 electrons and they're all entangled in some large quantum state, you're probably not interested in that as an ordinary person. So it's not human information. There's no semantic meaning to that. However, we still call it information because in the sense of technical information, it's still considered as bits, because when you measure those 20 particles, what do you get? You get a series of 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1. You still get bits at the very end. So we call it information. But that information has no meaning to a person. It only has a meaning to another quantum computer. So one quantum computer can generate 20 qubits in some entangled state. We call that information. My job is to transmit that quantum state by teleportation to another distant quantum computer. And the other computer takes that quantum state in and can use that quantum state to do a job. So the receiving quantum computer says, oh, that's wonderful. Thank you very much. I really understand exactly what that quantum state is going to be used for. But a human wouldn't know that. Okay, so it's information transmission between two quantum computers. That's the answer. All right. Reading more questions here. let's see. So one question is, will individual measurements of state X with Professor Xavier and the one with Bob yield the same result? So the answer is yes, but there's no way to know that's true. The only way you could tell that it's true is repeat the experiment many times. So on a single trial, Professor Xavier does not make a measurement. If he did a measurement, he would destroy the state. So instead, he transmits that to Bob, and Bob can make a single measurement and get a result. Now, the results are only predicted by probabilities. So I guess I have to back up and say the answer was no, actually. Yeah, that's right, because Professor X cannot measure the particle. And even if Professor X knows the state, he can't predict exactly what outcome he'll get when he makes a measurement, right? He can only predict probabilities. So Bob does have the same exact probabilities that Professor X has, but the measurements they would get, if they could both measure them, would not necessarily be the same. So it's not the measurement outcomes that you're transporting, it's the quantum state that you're transporting. And as I said, humans don't care about that, but two quantum computers do care about that. Let's see. Somebody asked about joint measurements. Is there a classical analog to joint measurement? And it's joint measurements not so useful in classical statistics because you could just make individual measurements and you would know everything. But in quantum mechanics, you can't always do that, or you don't want to do that. And so it plays a special role in quantum physics that does not play in classical physics. The question is, when Bob receives the photon, what is the controlled transformation box? Right. I didn't say what that was. So here it turns out that if the photon B has a particular polarization, although Bob doesn't know it, he can transform it in a controlled way by putting it through a new kind of a crystal. There's special kind of crystals that can rotate polarization by a known amount of angle. So depending on what, so Bob has a collection of 4 crystals. Each one would rotate the polarization by a different angle. So when Alice calls him up and says, okay, use crystal number 3, Bob throws in crystal number 3 and it does a controlled transformation. So Bob knows what the transformation is, but he still doesn't know necessarily what the state is because he doesn't know the state. But if you do it a million times and compare everything, then you can prove that Bob did receive the correct state, the same one that the professor sent. Okay, and yeah, the particle A has also been sacrificed when Alice does the measurement. Yeah. Okay, so I think we have to move on here. We're almost at 3 o'clock in Oregon, where I live. Okay, thanks for all those questions. They're fantastic. So let's move on now to part 4, the quantum internet. We will attempt to explain how all these physics principles are used to actually build, at least in theory, a quantum network that can distribute entanglement or send entanglement over large distances, even though, remember, photons don't survive after 1,000 kilometers. So in a fiber, and satellite transmission is inefficient. So how can we overcome those problems? It turns out it's very tricky, and it's taken 30 years for physicists to figure it out. So first of all, what is a quantum internet? Well, point number 1 is we don't have a quantum internet, but if we did have one, it would be a network to distribute quantum entanglement to any 2 or more locations, regardless of their distance. So all the way out to the planet Jupiter, for example, or Pluto, if Pluto is really a planet. Secondly, a network should be interoperable. That means it's agnostic, or it doesn't care about the particular hardware used at each location. That's actually the meaning of the word internet. The word inter, when you speak of the internet, it means interoperable. So, I can use one computer platform like a Mac, and other people can use Windows, or somebody can use any other platform. And there's always translation protocols that translates one to the other. And there are also different networks. So you have network of networks, and each different network might use different protocols, but there's translation software. So everything looks transparent. We want to do that in quantum. So for example, you can encode qubits in photon polarization, or you can encode qubits in spin of an electron. Those need to be interchangeable so that the whole system becomes interoperable. Okay, thirdly, you need to have a classical control system to coordinate the system. So you're not going to eliminate the classical internet for two reasons. One is quantum networks cannot do lots of things that we like to do, like just sending emails or doing lots of just ordinary things that we currently do, like gaming, high speed, computer processing for running games. Those things will not be improved by quantum computers and will not be improved by quantum networks. But the other things that are improved, I'll talk about at the end here, things like privacy and identity verification and secure voting and all kind of other things that a classical network probably cannot do. Okay. So one example, which I'll have to go through fairly quickly because time is short, is quantum cryptography. So we have a problem of privacy. Alice wants to send a message to Bob. They want it to be secret, but the eavesdropper, evil eavesdropper here, can intercept the message and decode it. And if the eavesdropper is very clever, she'll try to do that in a way that Alice and Bob are not aware of her activity. Okay. So there needs to be a key system. Here's how the key system works. So Alice writes a message and she types it into the computer, says, "Hi, Bob." Now she also has a key. I'll tell you what a key is. They have the same key. So before they did this whole message business, they somehow shared the same key. See, those keys have identical patterns on them. So Alice can lock it and then Bob can unlock it. Now, the next thing, the key is used to encrypt the message. So the encrypted message down here looks like gibberish or garbage or nothing. Only if you know what the key is could you unscramble that and reconstruct the message. So now this scrambled message or encrypted message is sent across the public internet, and anybody can intercept it if they want, but it doesn't do them any good because they don't have the key. Now Bob receives it. Bob has the key, so he can decrypt it and get the message. If the eavesdropper intercepts it, too bad, she doesn't have the key. It works perfectly. This method works perfectly, no need for quantum. So why do we need quantum cryptography? It turns out the problem is not down here. The problem is in sharing the key. How does Alice and Bob get the same key? Well, the way it's done now, between say one politician leaves their city of operation, their capital, and goes to another country. They want to send messages back and forth secretly. What they do is, before the diplomat leaves their home country, they make 2 copies of a hard disk. And the hard disk has billions of keys in it, which are just strings of zeros and ones. And then the diplomat takes one of the hard disks to the other country, leaving the other one back home. There's a law, international law, that every country agrees they're not going to mug or the diplomat and steal a hard drive. That's called diplomatic immunity. So now they have this secrecy of having these shared keys. But now here's the problem. Why doesn't that work? Well, what if it's a satellite? And the satellite has to have trillions of keys in it, because you can only use a key once. If you use a key twice or 3 times, it becomes insecure. So once the satellite has a billion or a trillion keys, they use them up. After sending trillions of messages, no longer have keys, so satellite is dead, can't do anything. So how do you distribute keys to a satellite in a secure way Turns out that's where the quantum comes in. The quantum is used for distributing the keys between two places in a very secure way. And it basically relies on the fact that if the eavesdropper intercepts the key, which are qubits, and measures it, it changes the state, as we've already understood, right? You can't measure something without changing the state. So if the eavesdropper changes the state and sends that changed state onto the other person can detect that there's been some tampering going on, and they can do certain things to either shut down the channel, or they can do other things to try to get around it. So it's a way of detecting the presence of an eavesdropper, which you could not do in a classical system. So that's the whole story, and I'm going to skip over the details of how that's done. Okay. And skip over the details of how encryption is done very, very quickly. If I have an original message, some string of numbers, bits, and then I have a key, some string of numbers, I add them together some way, I get an encrypted message. I transmit that over to Bob. Bob gets that. Here's the encrypted message. He received, uses the key to decrypt it, and boom, get the same original message back. And it's all very simple mathematics how it's done. That's how the encryption and decryption works, but I haven't told you that how you distribute the key, right? How does Bob and Alice have the same key? That's the hard part. So here's how one way it's done. It uses quantum entanglement. So we're using exactly the same apparatus that they use to verify the Bell inequality experiments, where Alice has two measurement angles for the photons. You start out with a perfect Bell state, and Bob has two angles, and they make these measurements. And it turns out by doing very similar measurements to these, and by doing certain procedures, which I don't have time to explain, they can end up with a perfectly shared key. So they have the same string of zeros and ones on Bob's side as on Alice's side. And if the eavesdropper taps into either of these photon channels, Alice and Bob can detect that because there are changes of state that can be detected. So that's a very short description of a pretty long topic. This is for more details, you can see it in my little book that I wrote up here. Skipping these details here. Okay, let's go to a more deep physics issue here. Remember we said that John Bell can tell us how to create Bell states. And I gave the example of an atom that emits two photons. And I said it's automatically in a Bell state. But there's another way to create Bell states, which is extremely useful. And here's the other way to do it. We have some device, which I call entangling device. And I'll explain how that works in a minute. We start with two photons. Alice has one called A, Bob has one called B. These are the input to our device. The output can be in an entangled state if you do certain things, okay? So that's your device. So here's how the rules are for the entangling device, how they have to work. And I know how to build one of these, but right now I'm not going to tell you how to build it. So if here's how it works. If the B photon is H polarized, then the A photon's polarization is unchanged. However, if the B photon is V polarized, then the device has the effect of the A photon's polarization is rotated by minus 90 degrees. Thirdly, in all cases, the B photon's polarization is unchanged in either case. Now, this kind of looks like an XOR. If for people who are asking about XOR, this is called a quantum XOR. So go back and think about that. I'm not going to explain that further. But what happens here is the B photon, the state of the B photon controls what happens to the state of the A photon when it travels through here. That's why there's an arrow here. This lower one controls what happens to the upper one. Okay. So as Abby mentioned earlier, we can denote the state of polarization of photons either by letters, H and V, D and A, or by these little arrows that actually show the direction of the state vector on the piece of graph paper. Then the diagonal state is a quantum superposition of horizontal in superposition with vertical, and etc. Okay, so that's the setup. Now let's go into how it operates, examples. Okay, here's one example. In this example, so we're going to consider 4 cases, all right? The first case is that the B is horizontal and the A is vertical. Well, this rule says if B is horizontal, then A doesn't change. So nothing changes. So the state coming out is the same as the state going in. And I noticed that this can be written with an ampersand because that's the symbol that means combined with. It also means and. So A is vertical and B is horizontal. And again, I don't mean that the polarization is vertical. I mean the quantum state is vertical and this quantum state is horizontal. But now let's do the same thing where B is vertical. Now we know the rule says that A is going to be rotated by minus 90 degrees. So A was vertical, now it gets rotated minus 90. So now the state is A is horizontal. Sorry, A is minus, I'm going to call this minus horizontal as opposed to positive horizontal, which would be pointing in the right-hand direction. So minus horizontal and B is still vertical because B never changes. So I'll let you think about these 2 questions for a minute and see if you can fill in the blanks on paper or in your head. Okay, 5 more seconds. Okay, well, good. Okay, so great. So here's what it looks like. Notice that if B is horizontal, A doesn't change, so A is the same. But down here, B is vertical, and so A gets rotated by minus 90. So it's here, and it gets flipped up to vertical, going rotating minus 90 degrees. So now we end up with this state, vertical and vertical. Okay, so that's just the operation, the basic operation. But now comes the sort of magic trick. Poll question 13. Show this one, Abby, put that up. So I will read through this a little bit to give you time to think about it. So the input state, the input state of B, the B photon, is diagonal, as I show in the picture here. But remember, diagonal is the same thing as a superposition between horizontal and vertical. So we have both possibilities sitting here in the control photon. So now remember these rules here. If A goes in vertical, what's going to happen to A? What could possibly be the correct description of the outcoming state here? How's it going, Abby?
We're about 50%.
Okay, 5 more seconds. Click
Sorry, I
on
think my
something.
microphone is being funny. Were you able to hear me? We were about 50%.
I could hear you.
Okay.
You were quite silent, but quiet. Okay, let's look at the results. Okay, C, interesting. So people are claiming here that the output state is entangled because now we have a superposition of 2 different combined states, B and H in superposition with minus H, and V. Well, that's exactly correct. And I will illustrate why that is true. Here's the proof for those who weren't sure. So in this incoming state is this. It's this here, A vertical and B diagonal, but that's the same as here's the tricky part. You have to decompose the B part into a horizontal and a vertical. And tacked onto that for both cases is A vertical. So this state is the same as this second line here. And now you can see that each of these pieces of the state, each piece of the state transforms in the device according to the rules. So this piece of the state goes through unchanged because in this piece of the state, in this possibility of the state, B is horizontal, so A doesn't change. In this possibility of the state, B is vertical, so A gets rotated down by 90 degrees, so you know about that state. So that's true. So this is a very nice device because we start with 2 qubits that are not entangled, and we can create a known entangled state. And this is an example of a quantum logic gate, and a quantum computer would have many of these devices inside of it to perform logic operations like quantum XOR. And a quantum computer, has to be programmed. So you need to have hundreds of these devices and a program that's a sequence of operations. And of course, you need more than 2 qubits. You need 100 qubits. This device is called a C-naught gate. C means control, and naught means you flip. You change the state somehow. Okay. Now we can run this device backwards from right to left. It's a very cool thing. If I start with that same entangled state that was produced in the forward direction, and I run it backwards, it undoes the same operation that was done in the forward direction. So it reproduces this state. So I can verify that. If I start with this state, like Professor X gives me this state and says, I promise you I gave you this correct state. And I say, well, I'm gonna check you. So give me that state 100 times, and I'm gonna do 100 trials and see if I get the right probability outcomes. So what happens is this state goes through, and this A photon comes out vertical, and I put it to a calcite that's oriented to separate H and V, and it goes click right on the vertical channel. And the bottom one comes out diagonal. Now I do a trick. I use a diagonal oriented crystal. So it distinguishes between diagonal and anti-diagonal. So it goes click, I get D. And so I say, yeah, it's correct. You gave me the correct state. I only had to do it once to verify it. Or maybe that's not true. Maybe that could have just been a coincidence, right? That could have been an accident. So really, I need the professor to send me it 100 times. And if I get V and D every time out of 100, then I know the state was correct. And then I can believe the professor in the future when he says, I sent me that state. I say, okay, I trust you. So it's a verifier. And again, this shows some of the details here, which I won't go through right now. Okay, so this device can be used in 2 ways. It can create an entangled state, and it can verify an entangled state. Interestingly, for you who know classical computers, if this was a classical XOR, you could not do this, because a classical XOR only has 1 output, not 2 outputs. And the quantum XOR or C-naught gate has 2 outputs, and so it's reversible. And the idea of a reversible gate is very important in quantum computing. So this just shows that if the professor now tells me, I gave you one of these 4 possible Bell states, but I'm not going to tell you which one it is. I can find out which one it is. Now let me back up and say, what are Bell states? So I've always referred to this top state, BS1, as the Bell state. But it turns out there's 4 varieties of Bell states. You can H plus VV, or you can have HH minus VV. Remember, a simple phase change gives me a totally different state. We showed that for single qubits, but it's also true for double qubits. or we can have H and V plus V and H, or we can have H and V minus V and H. These are four distinct states, and I can prove they're distinct by testing it. And each of these states will give a different combination of detectors on the left-hand side. This state will give HD. This state will give HA. This state will give VA. This state will give VD. So they're distinguishable. Therefore, they are, uniquely physically different states. And we use these four states in quantum computing and in quantum communication. So I'm going to move on. Now we're going to use a joint measurement. And a Bell state measurement, which I just explained, is an example of a joint measurement. Because why? Because it took in two particles, A and B. It gave me some outputs, but it didn't tell me, what the state of A was or the state of B was. It only told me what the entangled state of the joint combination was. So that really is a joint measurement, this device here. And by the way, if we back up way far back into the teleportation discussion, this is the measurement that Alice uses to get four possible outcomes that she then telephones Bob and says, I got one or the other of these. And that's a Bell state measurement. That tells Bob then which controlled transformation device to put onto his B photon. So that, moving way back again to teleportation, this applies there as well. Okay, so measuring Bell states. We do a joint measurement, as I just showed. And this just shows sort of a physical setup. So we have two particles, A and B. They might be in some entangled state. And let's say that we know that they're prepared in one of these four states. We measure in the Bell state measurement, and it tells us which one it was. Okay. Actually, I said I won't attempt to explain here how it's done, but actually I just did on the previous slide. Good. And I said you can use it for teleportation, and that's exactly what's done. This Bell state measurement is the teleportation measurement, and here's the controlled transformation. And for good measure, I put in a quantum memories, and for even better measure, I put in what's called a quantum repeater. This little blue circle with the two red dots in it, that's a new thing now introducing called the quantum repeater. So to have a working quantum internet, you need all these elements. You need entangled states, which is a resource. That's not the measure. That's not the message. Remember, the message is the state X, which could be entangled with other things. It's a resource. So somebody has to give you these entangled states. You're going to use them to do teleportation. Then you need quantum memories, which can store the quantum states of A and B for enough time such that you can synchronize everything. But if this distance here is too large between the state source and Bob, you also need what's called a quantum repeater, which I'll discuss a little bit later, but not in any detail. I think other lectures in this winter school will describe how quantum repeaters actually work. They enable you to extend the distance over much more than 1,000 kilometers, 100 kilometers. Okay, so now why are they needed? I mentioned this before. If you have an optical fiber and you send light into it, every time the light ray bounces off of the inside of the optical fiber, a little bit is lost out the sides. No matter how perfect the fiber is, this always happens. It's a physics principle. It's not an imperfection. And so by the time you go 100 kilometers, the photon, if it's just one photon, it certainly has been lost. And this just gives a little table of how much is lost. After 80 kilometers, the power is decreased by a factor of 10,000. So if I just put in one photon, the probability that the photon gets through is 1 part in 10,000. That's very bad. You can't do anything with that. So you need some kind of quantum repeater, which you would insert in the middle of the fiber, and it would receive the photon state and then somehow regenerate it and somehow overcome these losses, which I won't tell you how that works. Now, we also need quantum memories for synchronization. I'm going to attempt to explain one example of how quantum memories would work. So let's go back to our atoms. Remember, we had those ions. which are an atom with one electron removed. And I talked earlier about energy states. I talked about if the atom is in the lowest energy state, let's say that's this one down here. Now there's other energy states that are higher energies, and some people think of those as orbits or orbitals, but we know the energy is quantized. This is the fundamental principle of quantum mechanics, that if you confine an electron, by the way, the atom started out with many, say with 2 electrons, and I removed one of them, so there's still one electron inside the atom. Okay. So we have this one electron, and because it's confined inside of an atom, its energy is quantized. It's kind of like if you have the body of a violin, and you know that the frequencies are quantized. When you hit the resonances of the violin body, you get a louder response. That's quantization of frequency. Here we have quantization of energy. So the electron can only exist in these discrete particular energy states. Now, it turns out that in certain ions, this energy state, the lowest one, has a clockwise spin electron. This higher energy state has a counterclockwise. I left out the arrow here. Okay, I should have an arrow there. Counterclockwise. So we can code a 0 quantum bit into this lowest energy state and a 1 quantum bit into the higher one. So to change the state, we just have to make the electron change from lowest energy to higher energy, or vice versa. Okay, that's how we encode states in the electron spin inside of an atom. Now, here's how we build a quantum memory. It's a little tricky, but just follow along. It's kind of fun. If we start with an atom in the lowest energy state, which I labeled G, which stands for ground state. It's like the ground floor on an elevator. And then we have this higher state, S, which stands for the storage state. You're storing the quantum information in that state. So, I mean, both states store information, but you need 2 states to do it. Okay, now what you do is you have an atom that's initially in its ground state. That's not storing, well, that's just like initializing, setting up the initial conditions. Now, if a photon comes in, this is your quantum information photon, it comes in and gets absorbed. At the same time, there's a laser. Laser has a strong electric field, and it can cause a transition from this higher state down to this lower state. So what happens is I absorb the photon, it's now gone, and I have the laser drive, I would say drive or create or force the electron to go into this state called S. So what I've done is I've transformed the electron spin from clockwise to counterclockwise. At the same time, I have removed my quantum photon that has come in as a signal. So that's how one photon coming in can change it. Notice that if this photon doesn't come in, even though I have this control laser running, it doesn't cause this transition. So the laser combined with the atom is a way to detect the photon and to store the information about, is the photon present? Yes. Or the photon, no, it's going to stay in the ground state. Okay. So the procedure for memory, you can write and you can read and you can store. So what you do is you have a photon, the green thing is a photon or no photon, and the laser writes it into state S. So if the photon was there, it goes up to state S, and then you store it for a long time, could be a few seconds. And then later you want to read it, you turn the laser back on and it drives the energy state to a higher state, at which point the atom emits a photon. And that photon is emitted out into free space and goes on its way. So you see a photon came in, it's absorbed, it's stored, and then it's released and it goes on its way. So it's like a buffer or storage, and it can be used for synchronization. And you can also have entangled states, but I won't get into that right now. Well, here's a way to create entanglement between 2 quantum memories. So quantum memory number 1 is an atom in the presence of a laser beam. Quantum memory 2 is a different atom in the presence of a different laser beam. They're both just sitting there, and the atoms are in the ground state. Now, if the source over here, my source of quantum information, emits a photon, and let's say it's depolarized. Well, it goes through my analyzer crystal and it gets into a quantum superposition of H and V. Remember earlier we talked about how to produce a quantum superposition of photon location. Well, here we have it, different locations of the photon. But notice it's not true that the photon goes either this way or this way. It's in a superposition state. And it only reveals kind of the outcome upon measurement. So these two paths of this split photon goes two ways, and it creates an entanglement between this memory and this memory. So now the state of the two memories is entangled. This is memory 1, this is memory 2, and this is again memory 1, memory 2. So we have the state S and G. That's a possibility. That's a possibility where this atom got excited to the S state, but this one didn't. But that's in superposition with the other possibility, G and S. So you see the fact that I could create entanglement between the state of these two electrons is proof that this state of the photon is location entangled. It's not either or. If this photon were in the either or state, it would not produce this entangled state of the two memories. Cool. So now we've also encoded or stored the state of this photon into these two memories, because the original photon had a depolarization. So that means that there's 50% probability that either of these memories could be revealed upon measurement to hold the photon. However, if this photon initially were in the V orientation, vertical polarization, that photon would definitely go to the lower memory and only excite this atom and not that one. So the state would not be entangled. It would just be the GS state, only this one. If the photon were only in the horizontal orientation, polarization state, it would go to this guy and would produce only this one, S and G, but not this other one. So you see, depending on what the orientation angle of this photon state is, it's going to produce a different entangled state. And in general, we could put coefficients like X and Y in front of these two pieces of the state. And the square of those two numbers, X and Y, would give the probabilities and would correspond also to the angle of orientation of this original polarization state. So there's a lot wrapped up into this one slide. I could break it down into 5 slides, but I'm not going to do that to save time. Moving along. Hope you get the basic gist of it. Now, how to verify that entanglement actually was produced? Well, there's several steps you have to do. First, you have to show that this photon didn't simply pass through the memories and not get absorbed. So the first thing you have to do is to put 2 detectors here. And then if both detectors do not click, then we know entanglement has been created between the memories, assuming everything else is perfect. Okay, so that's step 1. Now to verify that, you'd have to use something like a Bell state verifier. You'd have to then release the photons from both memory, well, one photon. The one photon is shared in a superposition between both of these memories. You'd have to release that entangled state from both memories, and then the emitted photon pieces could be put through some kind of a Bell state verifier. Okay, so we're getting down to our last few slides here. I'm going to try to show how you can build a quantum internet, in pictures, not in reality. I think that the next 1 and 2 lectures in this winter course will go into much more hardware details, exactly showing real hardware, how you do these things. So I'm just going to do it at the abstract level. Now that we see how to create and verify entanglement between pairs of memories, let's see how we can extend that entanglement over a larger range by using entanglement swapping. Here we start with a pair of memories 1 and 2, and a pair of memories 3 and 4, which initially are not entangled. If we carry out our entanglement efforts, we try this many times until we succeed in memory 1 and memory 2 being entangled. At the same time, memory 3 and 4 are becoming entangled. When both are verified to be entangled, we then take qubit 2 and qubit 3 when we perform a Bell state measurement on those two. This gives one of four outcomes, which are the Bell states. Depending on which Bell state we obtain, we know how entanglement swapping has occurred, and now memories 1 and memories 4 are entangled in a known entangled state. We can then use this idea to extend entanglement across a large chain of memories. So we define a node as a location with a laboratory in which there are two quantum memories, which are nearby physically. So we have many of these nodes, each containing two memories. Initially, nothing is entangled. And we start carrying out entanglement operations pairwise between memories that are in adjacent nodes geographically. And we continue that until we've verified that all of these chains have entanglement created between memories within the node pairs. Once we have done that, then we can carry out Bell state measurements here within each node, and this results in entanglement swapping. And eventually, when all this is successfully carried out, we have entanglement between the far left node and the far right node. Now we can extend this whole concept to create a grid of entangled memories and create a true two-dimensional network across some geographical surface area, for example, across an entire continent. So again, we initially start with a grid of memories that are located within nodes. Each node has 4 memories. Then we start to carry out in parallel at the same time entanglement operations between quantum memories that are in adjacent nodes, indicated by these dashed lines. We try this many times, and with success probability P, each one of these succeeds, but that P is small. So after some number of parallel attempts, we have partial success. We don't need complete success. We don't need every single connection to be successfully entangled. We only need to have enough paths so that Alice is entangled with Bob. And that is our initial goal. They start out unentangled, and now they end up entangled. And notice that here we have 2 possible paths that can link Alice and Bob with entanglement after we carry out this operation. Okay. So just to reiterate some of that, what could a global quantum network do? Okay. So you can distribute entangled states. That's the important thing. Quantum key distribution, blind quantum computing. What that means is that if you have a quantum computation you want to do, and you know what the program is, but you don't have a quantum computer, you don't want to transmit that information by email because that could be intercepted. So what you do, you build a quantum state, a bunch of quantum bits, and you teleport those quantum bits as I just showed, or transmit them by this entanglement distribution network over to, you first collect a bunch of entangled memories using the previous slide, the method on the previous slide. Then you use those entangled states to implement the teleportation protocol for many different photons. So then you can actually teleport your quantum state from your lab to a quantum computer in another city, in another lab. That quantum computer carries out the computation and produces not an answer, it just produces a new quantum state. And then they teleport that state back to you across the internet and the network. Then you make measurements on your quantum state and you get the answer. But that's all completely private, because if any eavesdropper intercepts all that, they destroy the state and they cannot tell what the answer was. So that could be very useful. Okay, database, global timekeeping, synchronization, improved sensing, all these different things can be done. So these are quite speculative because first of all, we don't have a good quantum computer. Second, we don't have a quantum internet. Thirdly, we barely have quantum sensors that are functioning. So this is all very futuristic concepts. But over the next 20 years, we think that much of this infrastructure is going to be built. And to be honest, the most useful applications of this infrastructure are probably not predictable by us right now. Just like every other thing that happens in computing, new applications arise after you build a system. So these are the ones that are kind of obvious that we think are going to be useful, but there should be thousands of other ones that are not obvious. So that's why we think it's worth pursuing in detail. We can also test physics like quantum gravity theory and so on. Okay, cool. So finally, I want to just mention some misconceptions. And this might be the simplest thing you might take away from this whole course today related to quantum networks. First, you cannot do faster than light communication by any known means, including quantum teleportation. Two, you cannot create causation across the distance. Teleportation does create a causation. It does change the state at Bob. But remember, I should say cannot cause instantaneous change across the distance. You can certainly teleport information, but that takes some time. So I'm going to edit that slide and say not instantaneous. Okay. Three, this kind of technology cannot increase the data rate compared to classical networks. So it's not a matter of getting more bandwidth or getting a faster speed connection across an internet. In fact, quantum communication rates will probably be very small because the information that you're trying to transmit is much more delicate than classical bits. And so it requires much more slow, careful operations. But the point is that if you can do it, even slowly, it enables you to do certain tasks that could not be done by any classical technology. Okay. So if you want to hear another 20 hours of me lecturing, one or two of you might, but if you do, you can go to this website here on YouTube, and I presented a lot of this in more detail in a short course I did for Harvard University. And it's at the same level, much of the same material, but just expanded. And you can find this link you can do a screenshot now if you want, or you can look at this later when we distribute the lecture notes. So finally, this will appear at the end of every short course this week, and it's an evaluation survey. So we really want to have your feedback, both positive and otherwise, about how you felt that today's lecture went. And we will put up a link. Brianna, do you want to jump in here if you're there? So I think that
Yes.
as soon as I close down this page here, a window should pop up and it will take you to the survey. If you can't do it now, then we'll also send you an email and you can do it online at a later time. So with that, we are sort of done, but I think there's probably more questions here in the chat window. Let me just answer one or two of those, but since we are over time, I don't want to spend much more time because I also want to get to the evaluation survey. So let me just see what we have here in the Q&A here. Yeah, one question, does it require an entangled state to do state teleportation? Yes. That's why I call entanglement a resource. It's a quantum resource. And in the future, if you have a quantum internet and you have, and you buy a service, you're going to be paying, the network provider a certain amount of money for every pair of entangled qubits that they send to you. Just like now, you pay money for every kilowatt hour of energy they send. In the future, you'll be paying money per entanglement pair. It's a very valuable resource, and it's required in order to be able to do state teleportation. Okay. And no, all the details are not clear, what I've explained. This is meant to be a very conceptual overview, and in this time allowed and given the starting point we started at, it was not meant to for every operation here to be clear. It's only to give a kind of a sketch picture. Okay. All these operations are very hard to do. Nobody's claiming it's easy. If they were easy, we would have done it already. This is why the world economies are spending billions of dollars to try to build these kind of systems. Let's see here. How long does entanglement last? It depends on the system you're dealing with. If you have two photons and they're entangled, and you were to shoot those photons off of the Earth into outer space, and they started traveling to different galaxies, if they were entangled when they left the Earth, they would remain entangled for 100 years until they finally reset at the other galaxies. They would go indefinitely, okay? There's no natural degradation of entanglement. On the other hand, if you have two electrons and they're both in atoms and they're entangled, they will lose entanglement very rapidly. After 10 to 100 seconds, they'll lose entanglement because everything jiggles around and there's thermal vibrations and other dephasing mechanisms. Okay. So yeah, there's many questions here. Sorry, I don't have time to answer all of these. Brianna, is there a way for me to come back and answer some of these after the fact?
Unfortunately, no, we won't have that ability. I can try and grab some screenshots, and then if there are further conversations, maybe we can get your contact information.
Yes, please try to record all of the questions in the Q&A if possible, to download those. I don't know if it's possible, but please do that if possible. That would be very helpful for us going forward. Even for next year, when we present this course again, we can see what kind of questions are the audience is really, asking.
Absolutely.
So there's so much material here that we just barely scratched the surface. I hope you found it more amusing than frustrating. But let's go on to the evaluation survey. So Brianna, I'd like to also thank Abby and Brianna for helping to organize and co-present this material. And I hope many of you can stay on for the remaining courses this week. So let's go to the evaluation.